Mars, the god of war and the source of man's science-fictional demise. It has fired our imagination for thousands of years. We know the dry, barren planet was once flowing with vast reservoirs of water, the sky thick and filled with clouds, and the tantalizing possibility of life. It is the only other place in our solar system that man might one day call home. We Earthlings have fired numerous probes and satellites towards the Red Planet. An invasion of sorts, not for conquest, but for knowledge. What happened to Mars? Is there or has there ever been life on the planet?
A fundamental question that needs to be answered is life as we know it on Earth, even the simplest type of microbial life, unique? If we were to go to Mars and we were to find evidence of early microbial life, or maybe even present life that somehow survived in the near surface, would it be the same as the early life that developed on Earth? That's a very fundamental question. Does life emerge generally in planets where the conditions for life are favorable, if we find out that they were favorable on Mars? Or might life take its own unique path in different environments and turn out differently?
We have bombarded Mars with satellites and landers, but there have been more failures than successes. The Soviets established 2 Mars orbiters, while NASA landed 2 Viking landers carrying complex analytical laboratories and searched for signs of microbial life. Their findings were inconclusive. Further missions to Mars still had a high mortality rate, but the successes were outstanding, with robotic probes operating for years beyond their initial missions. In fact, Mars is a planet occupied solely by robots on the surface and satellites peering down from above. All these instruments perform admirably in their specified fields of endeavor, giving us a much clearer picture of the planet and its history. The science was following the water, what happened to it, and where it is now.
Thanks to the specific instrumentation on board the mission, we are able to tell us what kind of ice did we find. And the result is that there is a mix of CO2 ice, or carbon dioxide ice, and water ice. And it's very important to characterize it, especially for the water ice or frozen water, because one of the main objectives of any mission to Mars is to trace the water on Mars in every form, liquid if possible, solid, water vapor. So it's very important to study the ice because it's one of the reservoirs of water on the planet.
The science was conclusive. There was water on Mars. There were ancient lakes and rivers, even an ocean. We needed to learn more. With the advancement of analytical technology, computer power and robotics, a new rover was constructed. Big, complex and heavy, it required a new way to land on Mars safely. Engineers came up with a system that couldn't be fully tested here on Earth. It required a lot of things to happen correctly, on time and in order. This was the Sky Crane, and the rover Curiosity was the first to try it out. A controlled re-entry with heat shield, aerobraking with a parachute, all pretty standard. Then a rocket-powered Sky Crane drops from the aeroshell and gently descends toward the surface, spooling out the rover below on cables. The rover touches down, cuts the cables, and releases the Sky Crane to fly off and crash harmlessly. The Curiosity rover has been an astounding success, traversing the terrain for over 10 years, taking samples, drilling and studying rock formations, zapping samples with a powerful laser, and photographing its progress.
Now, in the belly of that rover is an instrument called SAM. It's an instrument suite that has a couple different instruments in it that allow us to look at different types of gases. It helps us understand the chemical composition of the atmosphere and the end of minerals that might be found in the rocks and the soils on the surface. In particular, it helps us identify organic molecules that might be present.
So the sort of evidence we're looking for, sorts of signatures of past life that we would be looking for would be signatures of microbial life. So not realistically looking for dinosaur bones and that kind of thing. If life ever existed on Mars, we expect it to have been microbial, microorganisms.
Orbiters, including Mars Odyssey and Mars Express, have been hunting down life as well from orbit.
After 10 years of mission, we have achieved a global view of Mars, and then we know at every location on the surface if you find some special minerals or not. So we have really the global view that tells us the history of Mars. Mars Express has, for the first time, detected methane, and also the concentration in the atmosphere vary from a place to another, from a season to another. And this discovery has been very debated in the scientific community because, in fact, methane should not be there because it's being destroyed in the atmosphere by the ultraviolet radiation. So if methane is there, there must be a source of methane, and for the time being, the origin of this source is largely unknown.
However, with Curiosity prowling around Gale Crater, it too detected seasonal methane.
Now, methane has been found previously in the Martian atmosphere by both Earth-based telescopes and spaceborne orbiters. But this is the first time that we've actually seen a sharp increase and decrease in the abundance of methane in the atmosphere in Gale Crater. What this really means is that present-day Mars is an active environment.
The big question is, what is the origin of this methane now being released? The two principal areas are first, by analogy with the Earth, it could be released and produced initially primarily by biology. This would be microbial activity acting on certain chemicals below the surface and then producing methane as a byproduct. But of course we can't state with certitude that it is biologically produced. And so we also consider geochemical mechanisms in which carbon dioxide is actually combining with water and producing methane under very high temperatures and pressures. And that methane can then be released in the atmosphere separately.
Now, at this point, we don't have enough evidence to tell us whether or not the organics we're finding are biological or non-biological in origin. There are several viable non-biological explanations, including this organic material could have come down from space, from meteorites or comets, or organics can be formed by geological reactions in the rock itself. Now, what's exciting about this discovery is it gives us new hope in the search for chemical evidence of life. We found the organic material. Now, the next step is trying to figure out what its origin is.
Main engine start, ignition, and liftoff of the Atlas V with Maven, looking for clues about the evolution of Mars through its atmosphere.
The latest NASA orbiter mission is Maven. Launched in November 2013, it made orbit 10 months later.
Maven is the Mars Atmosphere and Volatile Evolution mission. Our goal is to study the role that loss to space has played in the history of the atmosphere. Where did the water go? Where did the CO2 go from the early planet? These are important questions to understand how Mars went from an early warm, wet environment to the cold, dry environment we see today.
There's evidence of water flowing on Mars at one point in time, perhaps even oceans on Mars. And what happened that it's so barren at this point in time? And a key part of that is the atmosphere, and it's a much thinner atmosphere than what scientists believe it was at one point in time. So the stripping away of that upper atmosphere, that's what Maven is going after, the climate change at Mars.
One of these processes is called sputtering, where atoms are knocked away from the atmosphere due to impacts from energetic particles. The sun constantly emits high-energy photons. When these enter a planet's atmosphere, it can crash into a molecule, knocking loose an electron and turning it into an ion. When this happens in the presence of a magnetic field, the ions are captured and spin around the field. Conveniently, the sun generates a giant magnetic field that is carried by the solar wind. As the magnetic field sweeps past the planet, these ions are carried away. Depending on where they form, other ions will not be carried away but will hit the top of the atmosphere. These ions crash into other molecules and fling atoms everywhere. Some of these atoms can be knocked or sputtered into space, causing atmospheric loss. As this process continues over billions of years, Mars' atmosphere has disappeared, and along with it, the water. How much water has Mars lost this way?
We used the world's 3 major telescopes for infrared astronomy. From the ground, we could actually take a snapshot of the whole hemisphere of the planet on a single night.
Water naturally carries a heavy isotope of hydrogen, deuterium, which remains trapped in the water cycle while normal hydrogen is lost to space. Detecting the amount of deuterium enrichment tells us how much water has been lost.
Now we know that Mars water is much more enriched than terrestrial ocean water in the heavy form of water, the deuterated form. Immediately, that permits us to estimate the amount of water Mars has lost since it was young.
So in the ancient past, we have some indications of water was flowing on the surface, but how much water was there? We're talking about oceans, are we talking about small rivers, little rain? So these definitions of how much water was on the planet was very undefined.
A major question has been how much water did Mars actually have when it was young, and how did it lose that water?
The findings indicate that only 13% of an ancient ocean remains on the planet today, now stored in the polar ice caps. 87% of this ocean has been lost to space. This means that early Mars would have looked much different than it does today, with a significant portion of its surface covered by water.
So the really interesting question is, could it form a sea or an ocean? And indeed, it would. In the northern plains, which is a relatively flat region but depressed from the rest of the planet, it would form an ocean that was approximately 20% of the planet's surface area. And so that is a respectable ocean.
This ocean had a maximum depth of around 5,000 feet or around 1 mile deep. It's deep, not as deep as the deepest points of our oceans, but comparable to the average depth of the Mediterranean Sea.
By combining Martian topography with the new estimate for water loss, the researchers were able to simulate Mars's ancient ocean and its escape to space. As Mars lost its atmosphere over billions of years, it lost the pressure and heat needed to keep water liquid, causing the ocean to shrink and recede northward. The remaining water eventually condensed and froze over the north and south poles, giving Mars the ice caps that we see today.
We now know that Mars was wet for a much longer time than we thought before. Curiosity shows it was wet for 1.5 billion years, already much longer than the period of time needed for life to develop on Earth. And now we see that Mars must have been wet for a period even longer.
It's fascinating that we can learn so much about 4.5 billion years ago what measurements are taken right now. And ultimately we can conclude this idea of an ocean covering 20% of the planet, which opens the idea of habitability and the evolution of life on the planet.
Building on this knowledge, scientists are developing the next series of robotic probes to be sent to Mars in the coming years. This time, NASA is building on its successes, utilizing hardware and systems that they know will work.
We've been to Mars before with the JPL Lockheed Martin team. We've been to the surface of Mars before successfully with Phoenix. We know how to operate the arm. The surface operations are much, much simpler than Phoenix. We're putting 2 instruments on the surface and then we're leaving them there with no ground-in-the-loop interaction, repetitive weekly uplink downlink sessions. We're just made to do this mission.
The InSight mission is a geophysical mission to Mars. It's going to go to Mars and take its vital signs. It's going to take its heartbeat, the seismic activity of the planet.
So we're going to be doing that using a seismometer, a very high precision seismometer, using techniques that have been well developed on Earth to get the understanding of the crust, mantle, and core and sort of the relationship between those.
It's going to take its temperature by measuring the thermal gradient of the surface, which tells how much heat is coming out.
We also have a heat flow probe, we call it HP cubed. And what that does is it's going to basically take the temperature of Mars, and from that it'll be able to understand what the thermal flux is over the course of a full Martian year.
And it's going to sort of measure its reflexes by looking at how the rotation wobbles with the tidal effects of the sun.
Our final experiment is called RISE, and that's going to be looking at basically the wobble of Mars to help understand what the core size may be and composition.
The European Space Agency is also well along with ExoMars, a rover with advanced drilling capability due to be launched by 2018. Its principal goal? To drill down deep in search of microorganisms.
What is new with ExoMars, with the rover in particular, is what we call the mobility. Mobility not only horizontal, but also vertical. And this is a peculiar thing that we have on board the ExoMars mission. So we will be able to sample material from below the surface. That is quite important to understand if there is any sign of past life activity on Mars.
We will be looking for the first time in the third dimension being depth. And we think that is where we have the highest chance of making an interesting discovery regarding the presence of organic molecules in Mars.
It's a whole planet out there with a complicated history. That history is a story that's stored in the rocks, and our job is to figure out that story and what that story of that planet tells us about this planet that we live on.
So where Curiosity takes rocks and grinds them up into powder and looks at their bulk constituents, what this mission would need to do is be able to look in a microscopic level and examine the rocks for these very tiny and detailed messages that they would be sending to us about the past life that could have lived there.
This that I'm holding up here is a classic biosignature from the Earth. It's a fossil. We're not actually expecting to see a fossil of shells or other components, but what we want to be able to see are, with this instrumentation, are the fine scale layering that one might see in a rock, in which we can see dark and light toned layers. And those dark and light toned layers are telling a story.
When will NASA send astronauts to Mars?
4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
The first test flight of the Orion crew capsule is complete. The hardware and systems are ready for mass production. The components, the engineering, the manufacturing are all underway, with NASA looking back to what worked in the past and utilizing it for the future. The solid rocket booster technology straight from the space shuttle has been extended and tested. NASA's new Space Launch System, or SLS, is coming closer to fruition, reusing the space shuttle's main engines as the new system's workhorses, saving billions of dollars and years in research and development. The Europeans are teaming up with NASA to provide the service model for Orion, allowing for long-duration, deep space flights. Autonomous Martian landing systems are well advanced and being tested. Software and hardware are fully integrated for both manned and unmanned Martian landings. And when they get there,
Desert RAT stands for Desert Research and Technology Studies. This is a group of engineers and scientists.
We're looking to test out new concepts, procedures, equipment, like rover concepts, to see how they work in the field environment.
So the team tests these technologies to make sure that in future human spaceflight missions we'll be able to do science as best as we can. That's something that NASA's never done, two human rovers at the same time. So we're really trying to develop how do you use these assets at the same time, and interesting things that you might not think about are your communications. So you potentially have 4 astronauts talking all at the same time to mission control or science communication background.
It's just like running a real mission, say, like you can think about the Apollo mission to the moon. You had the astronauts to the moon and you had the people mission control, but there was a science background you didn't hear about, but the astronauts were getting information from them.
Arizona has a very good climate for these types of analog studies. You have pretty much open plains and you have a lot of geological features that are analogous to places on the moon and on Mars.
long-term space voyages are being replicated on the ground and in orbit with the ISS. Surface habitats, power systems, food and oxygen supply manufacturing are also on the drawing board.
The human flight component would like to see an experiment where resources on the surface of Mars, from the rocks or the atmosphere, could be used to generate fuel or other parts that would enable future exploration in cutting the tie, so to speak, to Earth. So you wouldn't necessarily have to bring everything with you. You can actually manufacture it on the planet. And that's a really exciting additional component that we've been exploring and analyzing in this work.
NASA isn't the only one with its eye on this prize. ESA and now the Indian Space Research Organization have a spacecraft orbiting Mars, and they did it on their first attempt. Private enterprise is hard at work as well. Mars 500, Mars One, the Mars Society, Mars Foundation, and the Mars Initiative, to name a few. And they have volunteers lining up already for a one-way trip to Mars. It is inevitable that we will set foot on Mars in the very near future. We will stay and learn her secrets. Perhaps in the future we will be able to alter the atmospheric density through terraforming and return Mars to the world that it once was, awash with oceans and rivers, clouds and rain. Maybe some of us could call it home. There are many worlds within our solar system. Most reside beyond the asteroid belt. These are the moons of the gas giants of the solar system, each a unique and mysterious world of its own. Some have oceans of water, geysers of sulfur, or atmospheres of plastic. Some are just now being seen at the outer rim of our solar system. All are worthy of much more scrutiny. Currently en route to the Jupiter system is the scientific probe Juno. It will be the first orbiter mission to Jupiter since the troubled Galileo spacecraft in 2003. Its task? To establish a highly elliptical polar orbit and study Jupiter in the greatest detail so far. Several other probes have made flybys of the system en route to other destinations. Some of these return fascinating data on the Jovian moons. Jupiter, the largest planet in our solar system, has, as far as can be ascertained, 67 orbiting satellites. Most of them are odd-shaped rocky masses, probably asteroids like Amalthea, trapped in the massive gravitational field of the planet. However, there are 4 major satellites of Jupiter, each large and dense enough to form spherical bodies. These are called the Galilean moons, named after the great Italian scientist and astronomer Galileo Galilei, who discovered them in 1610. Io is the smallest of the Jovian moons, though somewhat larger than our own moon and closest to orbit Jupiter. The intense gravitational effects causes the violent and active nature of the moon. It has over 400 volcanoes, lava flows, and plumes of sulfur 300 kilometers above the surface. The most dense of the 4 moons, Io is also the driest. Io is thought to be composed of mainly silicate rock with a molten core of iron or iron sulfide. Most of the surface is composed of extensive plains coated with sulfur and sulfur dioxide frost. The surface is geologically young, which accounts for the lack of impact cratering. Unlike all the other planetary bodies, these craters have been covered over by volcanic activities. Numerous active volcanoes also eject material high above the moon and into orbit around Jupiter. The internal energy for this overactive moon is due to gravitational tidal forces between Jupiter and the other moons orbiting further out from Io. Just slightly smaller than our own moon, Europa has an icy crust covering what is believed to be a salty global ocean capable of sustaining indigenous life. It also has active geysers ejecting material into space.
So how do we think we know that Europa's ocean exists? Well, it's a combination of using telescopes on the ground and having spacecraft that have flown by Europa and collected data about the surface, about the interior structure, and about the magnetic field around Europa. And the combination of those data sets leads us to a high degree of confidence that this global liquid water H2O ocean is there today, and it's been there for much of the history of the solar system. And here's where Europa is a real game changer. It is far, far out from the sun, and yet it's got this liquid water ocean. And the reason that Europa has liquid water is because it's orbiting Jupiter, and the tidal tug and pull causes Europa to flex up and down, and all of that tidal energy turns into mechanical energy, which turns into friction and heat that helps maintain this liquid water ocean beneath an icy shell. Along with helping maintain liquid water, we think that tidal energy may also allow that ocean to interact with rocks on Europa's seafloor. And it may even give rise to things like hydrothermal vents, which could help provide not just the building blocks for life, but also the energy for life.
Europa is the most likely place to find life in our solar system today because we think there's a liquid water ocean beneath its surface. Now we know that on Earth, Everywhere that there's water, we find life. So could Europa have the ingredients to support life?
We might be actually looking at a body that is presently alive, presently active, and presently undergoing its geology. There is too much evidence right now lying around on the surface, the red stuff, that suggests that something's going on there. Is that an environment that is habitable for any sort of life form? By golly, we really have got to go back and figure that out.
We have designed the Europa mission to take a spacecraft and its set of instruments all the way from planet Earth to Jupiter.
Previous mission concepts were for a spacecraft that would orbit Europa, but Europa is bathed in radiation from Jupiter. Any mission that goes in the vicinity of Europa is cooked pretty quickly. Instead, we're looking at a mission that will orbit Jupiter, make close flybys of Europa, and then zip out of the high radiation region. This allows us to have a mission that's many years long and to collect and transmit lots and lots of data. As Europa orbits Jupiter, it flexes, and we could measure the gravitational change of Europa by encountering Europa at different points in its orbit. On a typical flyby, we would turn on our remote sensing instruments, we would image the surface, we would interrogate the surface with spectroscopy, and we would do the same thing on the way out. And we would essentially rinse and repeat, and do this many, many times until we understand Europa globally.
Images from the Hubble Space Telescope tell us that Europa might be emitting plumes of water high into space. If so, a spacecraft could fly through those plumes and sample it directly to understand the composition of Europa's interior.
If it does have the ability to harbor life, how does that work exactly? We'll have enough instrumentation to really pinpoint exactly how the mechanisms would work for replenishing the nutrients in a subsurface ocean.
Europa is so important because we want to understand, are we alone in the cosmos? If there's life in Europa, it almost certainly was completely independent from the origin of life on Earth.
And for the first time in the history of humanity, we have the tools and technology and capability to potentially answer this question. And we know where to go to find it. Jupiter's ocean world, Europa.
The Europa Clipper mission has passed preliminary development and strategy proposals and acquired further funding. The European Space Agency has been invited to develop an additional probe to ride along with the Clipper, as with the Cassini-Huygens mission, and either land or impact on the Moon's surface. The nominal Europa Clipper mission would perform 45 flybys of Europa at altitudes varying from 2,700 to 25 kilometers. A proposed launch window would be in 2025. If launched with NASA's new SLS heavy lift rocket system, the probe would take less than 2 years to reach Jupiter. Otherwise, it will be a 6.5-year flight. The largest moon in the solar system, and another icy world, is Ganymede. Composed of silicate rock and water ice, the surface is heavily pockmarked by impact craters and regions of tectonic movement. The moon has a thin atmosphere of oxygen and possibly ozone and atomic hydrogen. The moon has a liquid iron-rich outer core and an internal ocean with possibly more water than Earth's oceans. Most recent modeling suggests the interior may be layers of water and ice, like a club sandwich. Ganymede is also the only moon known to have a magnetic field. However, it is embedded within the powerful Jupiter magnetic field and overwhelmed. But there are indications of auroral activity on the moon. Ganymede is also the final target for the Jupiter Icy Moon Explorer, or JUICE, the ESA-designated mission to 3 of the Jovian moons. It will be launched in 2022 from Europe's spaceport in Kourou, French Guiana, on an Ariane 5, arriving at Jupiter in 2030 to spend at least 3 years making detailed observations. It will visit Callisto, the most heavily cratered object in the solar system, and will twice fly by Europa. Callisto is the fourth and most distant of the Jovian moons from Jupiter, and outside the main radiation belt of that planet. Unlike its sister moons, Callisto has a very thin atmosphere of carbon dioxide and molecular oxygen, and low radiation exposure. Callisto is composed of silicate rock and water ice, and may also harbor a subsurface ocean. It is considered the most environmentally acceptable location for a manned base in the future. Saturn has 62 confirmed orbital satellites, many less than 50 kilometers in diameter. The bulk of the larger spherical moons are predominantly water ice and a small amount of rock. They include Mimas, Enceladus, Thetis, Dione, and Rhea. Enceladus is covered in ice with a subsurface ocean at the southern pole. Geologically active in the southern region, geysers have been observed. This would be from tidal heating and orbital resonance with Dione and Rhea, and could contain a liquid ocean heated by internal radioactive decay. However, the prize of the Saturnian system is undoubtedly Titan. Titan is the only moon with a dense atmosphere, and, other than Earth, the only body to have stable bodies of surface liquid. It is larger than both the planet Mercury and our own moon. Cassini deposited the probe Huygens on its surface in 2005.
Titan is Saturn's largest moon. It's actually the second largest moon in the solar system, and it's the only moon in the solar system that has a large and substantial atmosphere. And that atmosphere in some respects is really similar to that of the Earth, being composed mainly of nitrogen, but in other respects it's really different. It has methane as its second most abundant gas, and that takes the same role as water vapor in the Earth's atmosphere. It evaporates from the surface, it forms clouds, and then rains down again, and in fact forms lakes that we see at Titan's North Pole, including ethane and propane and all sorts of complex chemicals. We also see these vast dune fields at the equator, which are not made of silicates as they are on the Earth, but actually made of organic substances, essentially plastics, which have actually sedimented from the atmosphere and are being blown around into dune fields, the same as we'd see on a desert on the Earth. And through this we can detect which molecules are in the atmosphere. We see all the molecules that were previously discovered by Voyager. But we're also able to look for new molecules, and in fact, buried within the signatures of these more abundant molecular species, we saw a very small spike, which was due to a new species which had not been seen before. And in fact, this was propylene. So the discovery of propylene on Titan is really exciting. First of all, it completes this chemical family where we have this missing link dating 32 years back to Voyager. But also it shows that there's much more there still in Titan's atmosphere to be discovered. Some people think that Titan is similar to the prebiotic Earth long ago, when the molecules were forming the basis of life. And we don't know what we're going to find on Titan if we send back further spacecraft with new instruments, more sensitive instruments, if some of the molecules on Titan could be similar to the basis of life on Earth.
NASA is preparing a new probe to follow in Cassini's footsteps. It is called the Titan-Saturn System Mission.
Cassini was able to look at the lakes, get a sense of the coarse composition of the lakes, but nothing about the organic molecules that are dissolved in the lakes. The Titan-Saturn System Mission is a 3-in-1 mission with an orbiter for Titan, a balloon that will float through Titan's atmosphere, and a lander that will splash down on one of the northern lakes of Titan. This mission will actually go into a lake, sample the liquid directly, see what the organic molecules are that are present. The Titan-Saturn System Mission also will go to Enceladus, a tinier moon, 1,000 times smaller than Titan, which has volcanoes, geysers essentially. that are spewing material from the inside of this moon outward. And it's a chance to see whether there might be molecules that would indicate that life has actually formed within the source region of these geysers. These geysers have water ice, and we strongly suspect that there's liquid water in the region that these geysers are coming from. We know there are organic molecules there because they've been measured by Cassini. The ability to follow this up quickly is essential because with Cassini-Huygens, we have now trained a generation of scientists who are ready to take a new generation of instruments and capabilities back to Titan and Enceladus and really answer the questions that Cassini-Huygens has left for us. And that continuity of knowledge and of enthusiasm is essential and very difficult to maintain in the outer solar system because trip times are so long. The Titan-Saturn system mission really is Jules Verne realized. It's a kind of planetary exploration that we have never ever done before anywhere else in the solar system and can only be done on Titan. This mission will touch the human heart in terms of the way it's exploring this fascinating world. It will be floating on the surface of a lake. It will be floating through the atmosphere. It will be revealing the entire surface from orbit at the same time. As we think of exploration, of unveiling a new world, it's exploration in the true sense of the word.
The planet Uranus has 27 known moons, grouped in 3 categories: 13 inner moons, 5 major moons, and 9 irregulars. Only Voyager 2 has passed by these worlds. There remains much to learn. The major moons in order from the planet are Miranda, Ariel, Umbriel, Titania, and Oberon. 4 of these moons have known internal processes such as volcanism and surface canyon formation. Miranda is the smallest of Uranus's round moons and one of the smallest objects in the solar system to be spherical under its own gravity. Strangely, it also has the tallest cliffs in the solar system. Thought to consist of equal parts of rock and ice, Ariel's surface terrain, probably of ice, is cross-cut with canyons, scarps and ridges. Umbriel is again thought to consist of rock and ice. Its surface is the darkest of the moons and heavily cratered. The surface seems to have gone through some form of surface heating that destroyed its very early features. Titania is the largest of Uranus's moons. Similar in composition, heavy cratering has been obscured by changes to the surface through some heating event like its sister Umbriel. Titania may have a tenuous atmosphere, as carbon dioxide and water ice have been detected on its surface. Oberon, the outermost of the spherical moons, seems similar to the others: ice and rock and heavily cratered. The surface has numerous scarps and graben from crustal movement. There are currently no plans to revisit these worlds. Neptune has 14 known moons, categorized into 2 groups, the regulars and the irregulars. The inner 7 moons orbit normally. The remaining half, including its largest moon Triton, orbit in either an eccentric, inclined, or retrograde motion. Triton orbits in the opposite direction to Neptune's spin. Scientists believe it was probably captured by Neptune's gravity in the early days of the solar system. Triton has an atmosphere that forms clouds and haze, and is the only moon closely observed by Voyager on its flyby of the system. However, Neptune plays a very important role at the edge of the solar system. The planets formed from a disk of dust surrounding our Sun billions of years ago. Remnants of this disk still remain: the rocky asteroid belt influenced by Jupiter and the icy debris cloud beyond Neptune.
Neptune creates a ring structure in the dust cloud which features a gap where the planet itself resides. And this gap should make it fairly easy to tell where Neptune is from afar, even at distances where the planet is too dim to detect directly. The supercomputer simulations that Mark Kushner and I performed also allow us to see what the dust in the solar system may have looked like when the solar system was much younger. In effect, we can go back in time and see how the distant view of the solar system may have changed. When we included collisions between dust particles, we were really amazed by what we saw. Dust collisions change Neptune's gravitational imprint. The gap in the ring structure disappears.
Over billions of years, Neptune shepherds the dust cloud into an outer ring to what is now called the Kuiper Belt. The New Horizons spacecraft is exploring this region with its first flyby of the enigmatic Pluto and its moon Charon. Charon is the largest of Pluto's 5 moons. The other 4 orbit in erratic motion around the Pluto-Charon pair. Nix and Hydra are both odd-shaped, contributing to their erratic orbital motions. This is Hydra, taken by New Horizons from a distance of nearly 650,000 kilometers, revealing its irregular shape. Pluto was the first of these trans-Neptunian objects detected and first thought to be a 9th planet.
And then Pluto was this kind of, odd guy out. It was this little object at the edge of the solar system. And then when we found all these other Kuiper Belt objects, this is kind of almost a 3rd type of object.
So for the first time ever, we'll be able to fly by a brand new object, an object that's been forming for billions of years, and understand what outer parts of the solar system are all about.
Pluto is the first of the Kuiper Belt objects, or KBOs, to be seen up close. There are many other KBOs, or dwarf planets, awaiting detailed scrutiny, such as Eris, almost the size of Mercury, and Quaoar, the first KBO discovered. The most eccentric orbit belongs to Senda, which has an elliptical orbit of 11,000 years, taking it to the icy Oort cloud at the edge of the solar system. The Oort cloud will one day become the new frontier. As scientists and astronomers peer more closely and with ever more fidelity at nearby stars, they are discovering exoplanets, worlds outside our own solar system. Stars with planets were once thought to be a rarity. They're turning out to be the norm and not the exception. With some confidence, scientists now calculate there could be as many as 40 billion Earth-like planets in our Milky Way galaxy alone. The first exoplanets were detected in 1992, orbiting a pulsar, the remnants of a massive exploded star that was now a fast-spinning neutron star. With data collected from the Arecibo antennae in Puerto Rico, Alexander Volshan discovered 3 terrestrial planets orbiting the pulsar PSRB 1257+12. Other pulsars have been detected with dust clouds and disks orbiting them. This suggests that these 3 planets are second generation. The original planets were destroyed by the stellar explosion, and the subsequent debris disk enabled these new planets to form. It was another 3 years before the first planet orbiting a G-class star similar to our Sun was identified, a gas giant like Jupiter orbiting 51 Pegasi every 4 days. 5 years later, another main sequence star was found to have multiple planets. Exoplanets were not easy to detect. They are tiny, their light smothered by the light of their star, and they are so far away. There are three main methods for planetary detection. The hardest is direct visual observation via telescope, both on the ground and in orbit. Some 59 planets have been discovered this way. More indirect methods are employed, one of which is the radial velocity method. As a planet orbits, its gravitational pull causes the parent star to move back and forth. This tiny radial motion shifts the observed spectrum of the star by a correspondingly small amount because of the Doppler shift. With supersensitive spectrographs, the shifts can be measured and used to infer details of a planet's mass and orbit. The 3.6-meter telescope at La Silla, Chile, has such a spectrographic instrument called HART and is the leading exoplanet hunter. This is Tau Boötis, one of the first planets discovered utilizing this method. 51 light-years from Earth, this planet is massive, some 4 times the mass of Jupiter. So far, over 600 planets have been detected by this method. Another observational tool, and the most successful to date, is the transit method. A planet that passes in front of its parent star relative to us produces a slight dimming of the star's light, which can be detected by sensitive instruments. Some 1,200 have been located this way. Until now, it was expected that exoplanets would orbit in more or less the same plane and in the same direction as the star's rotation. However, new results unexpectedly show that many exoplanets actually orbit at a large angle to their star's spin axis. In the case shown here, WASP-8b, the orbit is completely reversed. There are other tools and techniques in the planet hunting toolbox, including microlensing, occultation and TTV, or transit timing variation. Often more than one technique is used to verify findings. In fact, revisiting a planet after some time for verification can lead to surprising results, as in HD 189733b, a hot Jupiter-type planet. On revisiting it, Hubble discovered the atmosphere was being stripped from it by a violent stellar flare. With the Hubble Space Telescope dividing its valuable time between many varied tasks and objectives, a dedicated planet hunter called CORO was launched. The mission was led by the French space agency, CNES, with contributions from ESA, Austria, Belgium, Germany, Spain and Brazil. Launched in 2006, the mission lasted 7 years. It located 2 planets around the star CORO 7, one of which was the first found to display a density similar to Earth's. In all, it located 32 planets, and 100 others are awaiting confirmation. The NASA Spitzer infrared space telescope was launched to study protoplanetary and debris disks around stars and the curious brown dwarfs, often referred to as failed stars. Spitzer's infrared capability quickly led to numerous planetary discoveries and infrared mapping of other known planets, like hot Jupiter HD 149026b. Some 256 light-years away in the constellation Hercules, a planet dubbed a hot Jupiter, it is a sweltering 2040 degrees Celsius, the hottest planet yet detected, and also the darkest, reflecting no sunlight back into space. It speeds around its star every 2.9 days. A world just 2/3 the size of Earth, one of the smallest on record, and only 33 light-years away around the star GJ436, planet UCF-1.01 might be the nearest world to our solar system that is smaller than Earth. The planet, a rocky world, orbits so close to the star that the surface is probably molten. As with HD 189733b in the constellation Vulpecula, it appears to be tidally locked to its star, showing only one face as it orbits. Spitzer was able to distinguish the various temperatures of its clouds from 650 to 1700 degrees Celsius. Thermal imaging of these hot giants has provided more details of these distant worlds. In 2009, the game changed with the launch of the Kepler Space Observatory. As part of NASA's Discovery program, the Kepler Space Telescope was launched to survey and monitor a fixed field of stars of the nearby Milky Way trailing behind Earth. It observed around 165,000 stars, watching for any changes in their brightness. It has located over 1,100 planetary candidates.
Now, these are candidates, but most of them, I'm convinced, will be confirmed in the coming months and years. That's more than all the people have found so far in history.
A veritable menagerie of planet types is emerging, like Kepler 16b, orbiting 2 stars, ice worlds and water worlds like Gliese 1214b.
The Kepler team announced today 1,094 new planet candidates, bringing the total roster up to 2,326. Of those, 207 are Earth-size, and we now have 48 that are in the habitable zone, 10 of which are smaller than 2 Earth radii. So these are planets that could potentially be rocky. So it's an exciting milestone because we are really honing in on truly Earth-sized habitable planets.
The combined surface and space-based system observations have led scientists to believe that planets around stars are the rule rather than the exception, and the average number of planets per star is greater than 1. Kepler has discovered at least 86 stars with multiple planetary systems. Kepler 11, for example, has 6 confirmed planets orbiting a Sun-like star.
The Kepler 11 planetary system is amazing. It's amazingly compact, it's amazingly flat. There's an amazingly large number of big planets orbiting close to their star. We didn't know such systems could even exist. There are certainly far fewer than 1% of stars have systems like Kepler 11. But whether it's 1 in 1,000, 1 in 10,000, or 1 in a million, that we don't know, because we only know one of them.
The growing number of confirmed planets is opening up new insights into planet formation.
We're learning so much more about the orbits of planets, the masses of planets, the sizes of planets, and we're just beginning. Kepler is still returning data, and we're going to learn a fantastic amount about the diversity of planets out there around stars within our galaxy.
Around each star is a circumstellar region called the habitable zone. Sometimes referred to as the Goldilocks zone, this is a region neither too cold nor too hot, where a planet could, under the right conditions, support liquid water at its surface, and in turn could support life. The first Earth-sized planet in a habitable zone was discovered around a red dwarf. Named Kepler 186f, it is just 10% larger than Earth.
Kepler 186f is the first validated Earth-sized planet in the habitable zone of its star. It's the outermost of 5 planets to orbit a star that is smaller and cooler than the Sun. This planet orbits its star every 130 days, and so this places it in the habitable zone, where it's in a region where it could have liquid water on its surface.
The star Kepler 186 is 500 light-years from Earth in the constellation Cygnus.
This planet, Kepler 186f,
orbits a star that's cooler and dimmer than the Sun. So while we may have found a planet that's the same size as Earth and receives a similar amount of energy to what Earth receives, it orbits a very different star. So perhaps instead of an Earth twin, we've discovered an Earth cousin.
Believed to be a rocky world, its mass and density are yet to be determined.
This is one of the big milestones that we've been looking for in our attempts to find out if there are places just like home and if there's life out there. One of the big steps is to say, is there somewhere that looks, to all intents and purposes, like Earth? Well, we don't know just yet, but we know that there are places that at least look similar.
To date, over 48 Earth-like planets have been located within habitable zones. Gliese 581 has 4 known planets. The outer D planet is thought to be an icy planet that has migrated closer to the star and would thus be covered by a large and deep ocean. Kepler 62f is likely to have a rocky composition and is only 40% larger than Earth, making it the exoplanet closest to the size of our planet known in the habitable zone of another star. Kepler 62e orbits on the inner edge of the habitable zone and is roughly 60% larger than Earth. Other recent discoveries include Kepler 438b, 442b, and 440b, a super-Earth. The super-Earth exoplanet GJ1214b orbits its faint red parent star. This is the first super-Earth exoplanet to have had its atmosphere analyzed. It has a mass about 6 times that of the Earth and appears to be surrounded by an atmosphere of steam or thick clouds or haze. Based on observations, scientists believe that of the Sun-like stars, some 22% have an Earth-sized planet orbiting in the habitable zone. Assuming 200 billion stars in the Milky Way, that would be 11 billion potentially habitable Earths, rising to 40 billion worlds if brown dwarfs are included. Are any of these worlds close to Earth? In fact, yes. The closest star to our own is the well-known Alpha Centauri group, with the bright stars Alpha and Beta Centauri, plus the faint red star Proxima Centauri, the closest star to Earth. Alpha Centauri b is known to be orbited by an Earth-mass planet, making it the closest exoplanet to our solar system, a mere 4.37 light-years away, almost within our reach. Now in its 4th observing campaign, the Kepler spacecraft continues targeting 16,000 stars for exoplanets. It's estimated that the onboard fuel supply should last until at least December 2017. So far, Kepler has found an astounding 1,013 confirmed exoplanets around 440 star systems. The terrestrial telescopes continue to do the heavy lifting when it comes to verifying possible planet candidates. The HARPS spectrographic instrument at La Silla, Chile, is being joined by the Next Generation Transit Survey, or NGTS. It will search for transiting exoplanets with a focus on discovering Neptune-sized and smaller planets. NGTS is designed to operate in a robotic mode. It will continuously monitor the brightness of hundreds of thousands of comparatively bright stars in the southern skies. ESO's very large telescope at Cerro Paranal in Chile, composed of 4 individual telescopes, will be improved with the new next generation of adaptive optic system called SPHERE. Other improved technologies include the Gemini Planet Imager at nearby Cerro Pachon, now in operation, and the Subaru Coronographic Extreme technology currently being installed and tested. New, bigger and more powerful telescopes are in the pipeline as well. The 30-meter telescope planned for Mauna Kea, Hawaii, will have 492 small hexagon mirrors arranged together to form the primary mirror 30 meters across. The GMT, or Giant Magellan Telescope, will be built at the Las Campañas Observatory in Chile. It will consist of 7 8.4-meter mirrors arranged together to make up the primary mirror. Work on the mirrors is well underway. The European Extremely Large Telescope in the Atacama Desert is due for completion in 2024. It will have a 39-meter diameter mirror made up of 798 hexagonal mirrors and will be the largest ever built. It will enable scientists to study the atmosphere of exoplanets more closely. Space-based telescopes are advancing as well. The next generation infrared telescope, James Webb, is nearing completion as it goes through rigorous testing. A scheduled launch in October 2018 will put the 6.5-meter telescope in orbit as a replacement for the Hubble and Spitzer telescopes. Likened to the California gold rush, there are planets out there to be found, and the race is on. TESS, the Transiting Exoplanet Survey satellite, is scheduled to launch in 2017. TESS will scan the entire sky, searching for exoplanets using 4 state-of-the-art cameras. It will be able to determine the chemical compositions of exoplanet atmospheres. Also planned for a 2017 launch is Cheops. Its function is to characterize transiting exoplanets orbiting bright host stars. The satellite is a small package, roughly 1.5 meters square, with a life expectancy of 5 years. The European Space Agency has commenced a new program called Cosmic Vision, set to run from 2015 to 2025, with Plato, an exoplanet hunter, expected to be launched in 2024. Other projects underway include Pégase, under development in France, Exceed, the Exoplanetary Circumstellar Environments and Disk Explorer at NASA, and Finesse, the Fast Infrared Exoplanet Spectroscopy Survey Explorer, due to launch 2019. The Wide Field Infrared Survey Telescope, WFIRST, is another NASA observatory designed to perform wide-field imaging for the planet hunting community. It will be fitted with a coronagraph instrument for direct imaging of exoplanets and debris disks. Another NASA New Worlds mission is the Star Shade project, scheduled for a 2019 launch. It will physically block the star's light with a parasol to allow direct observation of exoplanets. NASA is already thinking about a future James Webb replacement. Called the Advanced Technology Large Aperture Space Telescope, or ATLAST, it will be 2,000 times more light-sensitive than Hubble. If all goes according to plan, ATLAST could be launched between 2025 and 2035. With these new tools and technologies, it is only a matter of time before we are able to detect Earth-like worlds capable of supporting life. Perhaps one day, even a planet emitting radio or other signals indicative of a sufficiently advanced intelligent civilization. Finally answering that great question, are we alone? The Moon, our closest celestial companion, our indispensable dance partner through the cosmos, lighting our night sky and gently tugging at our shores. Few have walked on her surface, but her allure remains strong. Once again, we are glancing her way with renewed interest and with a view to returning very soon.
Tranquility Base here. The Eagle has landed. Roger.
When I was a little girl and people were always asking me, what do you want to be when you grow up? And I used to always go, I want to work up there. As an engineer, you dream of a job like this where you get to follow in the footsteps of some of your childhood heroes. And of course, for me, the Apollo missions, seeing these folks on TV step on the moon and work for NASA, as an engineer, it's just a dream to be able to say, you know, I want to do that too, and here I am.
Only a dozen Americans have kicked the dirt on the lunar surface. It was a bold and dangerous engineering achievement driven by a political agenda.
The Apollo program was important because it showed that we could leave our home planet and visit an object like the moon. However, what we want to do next is learn how to live and work off of our home planet on another planetary surface like the moon. By developing this capability, we'll be able to know how to go throughout the inner solar system, which has many important destinations, both for science understanding and also may have economic importance for not only our generation, but for future generations.
The Soviet Union and the US had peppered the lunar surface with soft and hard landing spacecraft. The Soviets' Luna 24 was the last of that program, returning soil samples that contained traces of water. Much of science and technology has advanced since the 1970s. The mechanism of world politics has evolved, new partnerships have formed, new players are looking skyward, and more recently, private enterprise has taken up the challenge. With the faintest of inklings that there may be usable water on the moon, a forensic focus has turned to the southern polar region. Scientific programs in the 90s refocused on the moon. Japan was the first to revive lunar research and only the third nation to achieve lunar orbit with Hi-10 on a dust-collecting mission. The US followed with Clementine, a joint NASA military project. It completed a mapping survey of the lunar surface along with gravitational data and evidential proof of possible water ice hidden in a south polar crater in permanent darkness. 4 years later, Lunar Prospector mapped lunar resources, gravity and magnetic fields. It was also impacted into the southern region of the surface to elicit more evidence of water ice hidden in the craters. Europe's contribution to this resurgence in lunar exploration began with the launch of Smart 1. This tiny, ion-propelled satellite catalogued key chemical elements on the surface. It also enhanced the theory that the Moon was the result of a collision between Earth and a smaller celestial body called Theas some 4.5 billion years ago. Japan's second probe was Selene, better known in Japan as Kaguya. It continued extensive observations of the lunar crust and also carried the first high-definition cameras into lunar orbit, giving us a clearer picture of the rugged surface. Another proof of capability, this time by India. It also carried a NASA mineralogy mapper and an impact probe. It played a key role in the confirmation of water hidden in the southern lunar pole. 8 months later, NASA launched the Lunar Reconnaissance Orbiter, or LRO. It has spent the last few years mapping and scanning the lunar world with sophisticated sensors and continues to return a wealth of data.
The Lunar Reconnaissance Orbiter is, as its namesake says, a reconnaissance mission to the Moon. Our job is to take a suite of very powerful scientific instruments and make an atlas of the entire Moon, in some places in very great detail. Topography, mountain heights, mineralogy, temperatures, abundances of resources, including potentially the intriguing possibility that there's water at the Moon. We put all this together into a data set by flying low over the Moon for a year. This is the data that the people designing the human systems, designing the systems, picking the sites, need to take us back to the Moon.
This robotic mission commenced operations in June 2009. It was hoped the suite of sensors would fulfill several scientific goals, not only for the Moon, but as a framework for understanding planetary processes throughout the solar system.
The LRO instrument suite is comprised of 6 instruments and 1 technology demonstrator. And they are geared towards providing us a variety of data sets ranging from a thermal map of the Moon, global topography, and most importantly, looking for resources like water ice on the Moon. The entire suite should provide more of an atlas as opposed to a map, so that we know where to go on the Moon, where to have the safe landing sites, and where to put things like lunar outposts in the hopes of having human exploration in the near future.
The data being returned from LRO and the other probes draws a clear image of the evolution of the lunar surface and why it is composed of exactly the same elements as the Earth. After coalescing from the Earth-Theas collision, the proto-Moon cooled, then suffered several major collisions from orbital debris, which created many of the largest surface characteristics, including the mares. Cratering continued relentlessly over the millennia, drawing the familiar lunar vista.
My name is Lynn Carter. I'm a research space scientist, and I work with the Planetary Geodynamics group here at Goddard. I study the geology of planetary surfaces, the Earth, Moon, Mars, Venus. There's a lot of things you can learn about the Earth by studying other planets. For example, on the Earth, we have a lot of erosive processes. You know, it rains, it washes parts of the surface away. We have plate tectonics, which recycles the crust. But on other planets, those processes don't necessarily occur. So, for example, when we look at the Moon, we're seeing a surface that's much older. We can use impact cratering on the Moon to sort of understand how many impacts happened, the size of the objects that were hitting each other in the early solar system. One of my favorite things is to use radar remote sensing. For example, on Mars, we can use radars to sound all the way to the bottom of Mars polar caps and see all this layering within the polar caps. And on the Moon, we're using it to study impact cratering. Sometimes when an impact crater is formed, a huge sheet of melt is thrown out. This melted rock flows across the surface, but then over time, it's covered over by stuff from other impacts. But with the radar, it just blows right through all of that, and you can see this beautiful image of the melt flow coming out of the crater.
Launched with LRO was LCROSS, or Lunar Crater Observation and Sensing Satellite. It deployed sometime later than LRO and had a finite mission. LCROSS and the rocket stage that delivered it were deliberately crashed into the craters of the South Pole, whilst LRO orbited above and observed the impacts. The debris and gases thrown up from the lunar surface were closely studied by LCROSS as it too descended to the surface. The missions found evidence that the lunar soil within these shadowy craters is rich in useful materials. The Moon is chemically active and has a water cycle. Scientists also confirmed the water was in the form of mostly pure ice crystals, which had not seen sunlight for billions of years. LRO has continued to operate in polar orbit, making observations of the South Pole, and with repeated flyovers, it has drawn up a detailed map of neutron densities in the region, revealing where hydrogen and thus water can be found within the lunar soil. The importance of this discovery cannot be overestimated. Having this resource in situ means independence from the cost and effort of bringing water from Earth to the Moon. It can be used for creating rocket fuel, oxygen to breathe, water to consume and to irrigate crops, and used in other processes to manufacture building materials from the lunar soil. Launched in 2007, NASA's 5 Themis spacecraft have now successfully completed their 2-year mission to determine the cause of geomagnetic substorms. Because they are continuing to work perfectly, NASA redirected the outermost 2 spacecraft to the Moon. This new mission was called Artemis, and they studied the magnetospheric environment near the Moon. They also observed the effects of surface electric fields and ions from the solar winds on the lunar surface, and determined the internal structure of the Moon from variations in its magnetic field.
Well, in a nutshell, what we're finding is that the polar craters are very unusual electrical environments. Well, the solar wind is actually a relatively tenuous gas that's emitted from the sun, but it's not a neutral gas like the gas in this room. It's actually a gas that's really, for the most part, free ions and free electrons. So as you pass by, for example, a polar crater, the electrons will actually fill into the crater ahead of the ions. Now, as it turns out, as it does that, you create an electric field. It's called an ambipolar electric field, and that electric field then drives in the ions.
These hidden troves of water ice and other volatiles in the polar craters may be protected by a dangerous electric charge of hundreds of volts.
3, 2, 1, 0, and liftoff of the Delta II with Grail. Journey to the center of the Moon.
Grail consisted of 2 probes called Ebb and Flow. Linked together in a single flight path, they studied the gravitational field of the Moon, generating maps like this crustal thickness atlas. It reveals much about the interior of the Moon and even has some surprises.
2 years ago, we reported evidence that the Moon is shrinking. Now we've found evidence that the Moon is actually being pulled apart, forming features called graben. So the shrinking Moon, it turns out, is not shrinking everywhere. Some places the Moon is actually expanding by a little bit. So finding these young graben was a real surprise, because we thought, well, all these lobate scarps are telling us the Moon is shrinking. So what are these little small graben that are telling us the Moon is pulling apart doing in this picture? How does this all fit together? All that's related to how the Moon has evolved, how the Moon has lost heat. over its 4.5 billion year history. Most of the terrestrial planets, when they formed, were very hot, and they got so hot that they actually completely melted. When that happens, they will be in a general state of contraction because they're still hot on the inside and cooling down, and as they cool, they want to shrink. Only the outer part of the moon melted, forming what is called a magma ocean. And in that model, the balance of stresses or forces that are acting on the moon would allow us to form both these small lobate scarps that show contraction, as well as these small graben that show the moon being pulled apart. One of the really exciting returns of the Lunar Reconnaissance Orbiter mission is that we've seen this now growing evidence of very young geologic activity on the moon.
The moon's crust is much thinner on the near side, 68 kilometers thick on average, and varies from less than a kilometer under Mare Crisium to 107 kilometers thick just north of the crater Korolev on the lunar far side. The moon's mantle is only partially molten, and the moon's center of mass is offset by about 2 kilometers in the direction toward the Earth. This and other data quickly changed our understanding of the moon. To gather more evidence on the unusual electrical properties on the lunar surface and how it affects lunar dust, NASA sent LADEE, the Lunar Atmosphere and Dust Environment Explorer, to investigate.
At higher altitudes, we saw very few dust particle impacts, but the lower we went with LADEE, the more we saw, and it's a very steep rise. So if you're operating with spacecraft very close to the surface of the moon, as you would with a robotic lander or a human lander, you might need to consider the fact that you've got more dust there in the way as you come in.
This probe flew progressively lower and finally impacted on the surface.
Ignition, throttle up, main stage. That's it.
This is Morpheus, a robotic, self-guided lander. You tell it where to land, and it will do the rest, independently seeking the safest course and avoiding any rocky dangers. The ESA were also developing an autonomous lander to perform the same function.
The lunar lander is a small but very challenging mission. The most important part of it is, of course, landing on the south pole of the moon, which requires innovative solution concerning landing, hazard avoidance, navigation, and in fact, this is the mission which will bring about the new generation of navigation and guidance sensor, algorithm, and software.
But a fiscal year is a long time in space. NASA now have little interest in returning men to the moon. They are firmly focused on a Martian landscape. The Europeans have had budget cuts. The ESA lander now shelved for the time being. This leaves the door wide open for Russia and the younger players, China, India and Japan, plus several private companies now developing the same technology to put first robots, then humans on the moon. All this time, the Chinese National Space Administration, or CNSA, had launched 2 orbiter reconnaissance satellites, Chang'e 1 and 2. Then Chang'e 3 deposited a lunar rover on the surface. Their latest, Chang'e 5, made a return trip around the moon. They are firmly set on a permanent manned lunar base.
I think the reason this has resonated with so many people and all over the world, it's not just our country, is because everyone can look up in the sky and see the moon. And I think a lot of people remember the Apollo landings, the first, man on the moon, and you can also look up at the sky, and I believe that people, it's very tangible to them that way. The moon, they can relate, and so they want to be a part of it. That's my theory on why people have just so connected.
The moon is indeed a tantalizing prize. The Chinese have their lander and rover there now. Japan and India will be next. South Korea has an interest along with Russia, Canada, France, Italy and the United Kingdom. Private enterprise has had a prod with the Google Lunar X prize. The $30 million prize pales beside the glory of being the first private company to land a robot on the moon and to explore at least 500 meters and transmit high-definition images back to Earth. So far, there are 4 hot contenders. The Barcelona Moon Team, a consortium of companies headed by Galactic Suite Design. Their interests lie in space technology and industry with a strong focus on tourism. Penn State Lunar Lion Team. Faculty and students are developing a spacecraft to land on the moon, then lift off again and relocate to fulfill the prize requirements. Moon Express is a group of space and Silicon Valley entrepreneurs looking to mine the moon for its valuable resources like platinum, titanium, and the rare isotope helium-3. Finally, Astrobotic Technology, a Pennsylvania-based company with support from other companies including Alcoa and Caterpillar. They have already reserved a launch on a SpaceX Falcon 9 launch vehicle. Getting to the moon is one thing, staying there is another.
It was one thing to go for a handful of days in Apollo and go when you knew that the sun was quiet, or you hoped the sun stayed quiet, and you took the risk, you calculated the risk of cancer and such, and you made a short mission. You're going to live there longer, you need to understand it well enough to go, here's what I need to do to protect myself.
One of the things that we're looking for in the LRO mission is how the high radiation environment affects our ability to explore. So if we bring cameras or communication devices, how will they be impacted by the cosmic radiation? We need to protect our equipment as well as ourselves.
We want to be able to go back to the moon so that we can live there for long periods and work on the moon. So we need a mission that can help us find the best places to go and determine how to go back there safely.
Access to solar power continuously, that may be the first and most important reason over the near term. And then the possibility of resources being there. Those may take a much longer time before we're able to really exploit those. But the solar power is something we can exploit right away.
Whether it's water ice to have water, or potential minerals that we could use as raw materials to make into things that we would need.
All the major players have designed and planned many varieties of lunar bases. NASA, ESA, and private contractors have concepts on the drawing board. As more information comes in from the lunar satellites on the environment, resources, and dangers of cosmic radiation, these plans evolve. One of the latest is to use 3D printing technology. With all the challenges and difficulties, many have made firm commitments to establishing bases within 10 to 15 years. Some for scientific research, others for commercialization and tourism. Some would choose not to send test pilots and scientists, but stewardesses and sommeliers.
When we look back on what we did in LRO and we look at what followed, I think we'll see a profound impact. We'll see us as really being the small first step where we have human beings permanently off this planet, beginning to move out into the solar system, starting with the moon. As that pans out, I think we'll be a small piece of a profound development that when history looks back to say, this time we went back to the moon, this time we stayed, and we moved on from there.
As we continue to study the moon, our understanding of it improves, giving us new insights not only into how it has evolved over time, but also how other rocky planets in our solar system have come to look the way they do. With new missions, new instruments and new technologies, we will continue to improve our knowledge of the moon and better understand the history of our solar system. It rises in the east and bathes our planet in light. It powers the machinery of nature, our weather, encourages and sustains life on land and at sea, where it warms our oceans from pole to pole. When it sets in the west, it reveals to us its many billions of sibling stars, populating the night sky. We study our sun closely, and like a Rosetta Stone, it can reveal the secrets of all the other stars. You cannot study the sun in isolation. The influence of its power throughout the solar system it created is persuasive and dominating. The heliosphere is an immense magnetic bubble extending beyond the orbit of Pluto. It contains the solar wind of high and low-speed energetic particles and plasma that originate at the surface of the sun. After traveling for 36 years and 19 billion kilometers, the Voyager 1 spacecraft has reached the edge of this heliosphere.
Voyager 1 has left the bubble around the sun and entered interstellar space, the space between stars.
There, it still senses the shock waves emitted by the sun, which sound like this. To understand this source of power and its influences, scientists conduct observations from the ground and in space, where a flotilla of satellites train sophisticated sensors upon the sun and the space weather it creates.
Space weather is the field that studies how what's going on the sun affects us here on the Earth in our near space environment and on the space environment on other planets. The effects of space weather are so complicated because we have to understand what's going on at the sun as well as all that stuff traveling through interplanetary space, how that affects us here on the Earth and throughout the heliosphere, that we need an entire fleet of instruments to look at these various effects. It's basically a system science, so you understand one part of it in order to understand the other part of it, and you have to put that whole puzzle together to understand the full effects of space weather.
GOES-P is an ongoing series of Earth observation satellites that happen to keep a constant eye on the sun, monitoring this space weather.
So when the spacecraft's sitting in space, it's looking down at the Earth and it stays stationary like this. But this solar array out here moves and tracks the sun. So that way, it's always looking at the sun and can take a scan every minute.
The sun's outer atmosphere is constantly being heated up by the solar surface. And this causes particles from the sun's atmosphere to stream away constantly. These streaming particles, which are filling our entire solar system, are called the solar wind.
Different phenomenon from the sun is constantly bombarding the Earth. Although you might not know it, the solar weather affects you every day down here as well. Not only just astronauts, it affects people on Earth.
The latest generation of GOES satellite is the GOES-R, soon to be launched into orbit. Other low Earth orbiting platforms include ESA's microsatellite Proba-2, testing new technology, and PICAR, sponsored by CNES, the French space agency. Hinode is the Japanese word for sunrise. It is a joint mission between JAXA, NASA, and ESA to study the sun's magnetic cycles. Its close-up study has revealed the complex granular textures of the sun's surface and insights into solar flares.
A solar flare is a huge release of energy
that converts the magnetic energy of the sun into heat, into light. It accelerates particles and can really heat up the plasma in order of minutes to over 60 million Kelvin.
For a large eruption, the sun produces a flash of light, which we call the solar flare. It also produces a huge ball of material traveling away from the sun we call the coronal mass ejection. And both of those phenomena can accelerate subatomic particles, which we call solar energetic particles. These three things together make up a solar storm.
To study the solar wind phenomenon, a group of satellites were placed in a unique orbit between Earth and the Sun at what is called L1, or Lagrange point 1, a point of gravitational balance between the Earth and the Sun. The Advanced Composition Explorer, or ACE, observes energetic solar particles. WIND studies radio waves and plasma that occur in the solar wind and in the Earth's magnetosphere, and SOHO, the Solar and Heliospheric Observatory.
Using SOHO and using a technique called helioseismology, very similar to seismology on the Earth, we were actually able to see inside the sun. And so what we were able to do is see the layer of the sun just below the visible surface that we call the convection zone. And that's where all sorts of dynamics are going on. The inside of the sun is bubbling up to the surface. And that's really where all of the solar phenomena that we see is first developed. And so we were able to see underneath the surface and see these flows of solar plasma, see the formation of sunspots. And this is something that's never been done before. We're actually able to see the details inside of a star.
Another high-resolution space telescope was TRACE.
You're seeing details of the coronal loops. In the previous images you would from other satellites, it would look like it was just one big loop. And when you actually get to see TRACE, you can see it's all these teeny tiny, they almost look like threads. And there's these teeny tiny loops, and they're just breaking off and reforming and throwing plasma.
Using X-ray and gamma-ray solar flare imaging, RISI explores the particle physics behind solar flares. Another event subjecting the solar system to bombardment is the CME, or coronal mass ejection event.
A coronal mass ejection, or CME, is an eruption of plasma from the sun that shoots out into space, and it could affect us here at Earth if that big ball of plasma were to hit us.
NASA's twin stereo mission has one spacecraft orbit the sun ahead of the Earth and the other behind, providing a stereoscopic view of the sun to better understand these coronal mass ejections and the energetic particles of plasma.
Solar energetic particles are particles of plasma that are accelerated at the flare site from the energy that's released in the flare. And these particles could be accelerated up to almost 80% of the speed of light.
And a coronal mass ejection, when it's traveling so fast, creates a shock, and that can create solar energetic particles.
In 2009, NASA commenced a new scientific program called Living with a Star. The crown jewel of this program is the Solar Dynamics Observatory, or SDO, the most advanced spacecraft ever designed to study the sun and its dynamic behavior. The program's goal is to develop the scientific understanding necessary to address those aspects of the sun that directly affect us here on Earth. The spacecraft provides 16-megapixel ultra-high-definition imagery of the sun in 13 different wavelengths. From extreme ultraviolet frequencies to the helioseismic and magnetic imager and the atmospheric imaging assembly, each wavelength was selected to highlight a particular part of the sun's atmosphere. The results are stunning. They reveal fine details from the solar surface to the upper reaches of the sun's corona. These solar events dwarf our planet, and the science has brought a renewed focus back to Earth's protective magnetic field.
We are protected here on the surface of the Earth from solar flares and coronal mass ejections when they impact the Earth, due to the magnetic field of the Earth called the magnetosphere, which deflects the magnetic field and the energetic particles, as well as the atmosphere, which absorbs the higher levels of radiation.
Fortunately, we are protected here at Earth from flares and coronal mass ejections by the Earth's outer atmosphere. It absorbs a lot of the energy from the increased light from solar flares. But we're also protected by the magnetic field. You know, the Earth has a North Pole and a South Pole. Anyone who has a compass knows that. But this magnetic field of the Earth also protects us from these charged particles, the plasma coming from coronal mass ejections that largely deflects a lot of this direct energy. A coronal mass ejection will come and affect the Earth's magnetic field, and changing and hitting the Earth's magnetic field causes other changes on the actual far side, away from the Earth, that then accelerates more particles and shoots those particles then into the North and South Pole that produce these very beautiful waves of green and blue and red that are just lovely to see.
The sun is powered by a process called fusion, and that happens at the very core of the sun, where it is so intense, so hot, and so dense that protons fuse together and create helium. And this process fuels the sun and creates energy.
As the energy moves outward, boosted by magnetic fields, the temperature drops.
Up until that point, everything makes sense in that the hottest part is in the middle and everything gets gradually cooler as we move away. But then something very interesting starts to happen, which is that it starts to get hotter again.
This layer, where the temperature begins to rise again, is called the chromosphere. It lies between the photosphere and the corona, which is the hottest part of the sun's atmosphere. To discover how this corona is powered, another mission called IRIS was launched in 2013. IRIS carries a single ultraviolet telescope and imaging spectrograph, whose tight resolution allows it to see features as small as 240 kilometers on the sun's surface. IRIS's first images showed a multitude of thin, fibril-like structures that have never been seen before, revealing enormous contrasts in density and temperature occurring throughout the region.
The light from the chromosphere is difficult to interpret because of the complicated interaction that the light has with the matter. It bounces around, if you will, many times before its final bounce towards us. And this means that that interaction between light and matter needs to be modeled in great detail, due to not just advances in computational power of computers, but in the computational techniques that have been developed by the IRIS team. We are in a position to do this.
Data collected from the IRIS spacecraft has shown that the interface region of the Sun is significantly more complex than previously known.
Although the corona is extremely hot, millions of degrees, it's at a low density, so it doesn't actually take a lot of energy to heat it to that temperature. The chromosphere, on the other hand, is a much higher density, albeit lower temperature. And there's much more energy deposited in the chromosphere than the corona. So that a tiny fraction of that energy in the chromosphere escaping into the corona is plenty to power all of the processes that we see, from heating to such extreme temperatures to driving the solar wind that fills the whole solar system, impacting all the planets, including our own. We hope to better understand these fascinating and important processes with IRIS.
This energy streaming from the Sun causes other knock-on effects on the planets of the solar system.
The northern lights are particles that are being shot into the North Pole and the South Pole that produce these beautiful greens and blues and reds. They're not direct particles from the sun. a coronal mass ejection will come and affect the Earth's magnetic field, and changing and hitting the Earth's magnetic field causes other changes on the actual far side, away from the Earth, that then accelerates more particles and shoots those particles then into the North and South Pole that produce these very beautiful waves of green and blue and red that are just lovely to see.
Armed with more questions about the solar wind and energetic particles, NASA launched a pair of probes into Earth orbit. Named after the famous scientist who discovered the radiation belts surrounding our planet, the Van Allen probes were dispatched to study the radiation phenomenon and the magnetic fields around the Earth in greater detail.
During the course of geomagnetic activity, disturbances caused by flares on the sun, by big blobs of plasma coming out from the sun towards the Earth, the Earth's magnetic field is battered and shaken. Some of that energy is captured in the Earth's magnetic field, and through a variety of processes, that energy energizes particles in the Earth's radiation belts up to energies that are hazardous to spacecraft and astronauts. The two spacecraft are focused on the dynamic radiation belts in the Earth's inner magnetosphere. They're the only spacecraft that focus on those. Consequently, they're a critical component in the series of phenomena that link the Sun to the Earth.
Solar flares and CMEs are all driven by magnetic reconnection. This is where the sun churns up the magnetic field that's inherent in it, and then it causes oppositely directed magnetic fields to then annihilate. But you can't just get rid of magnetic field. You can't just get rid of energy. You have to convert that energy and transfer that energy into other things, such as plasma motions, accelerating the plasma, heating up the plasma, and also giving out more light.
We are protected here on the surface of the Earth from solar flares and coronal mass ejections when they impact the Earth due to the magnetic field of the Earth called the magnetosphere, which deflects the magnetic field and the energetic particles, as well as the atmosphere, which absorbs the higher levels of radiation.
But this magnetic field of the Earth also protects us from these charged particles, the plasma coming from coronal mass ejections that largely deflects a lot of this direct energy.
The phenomenon of magnetic reconnection is not well understood, so NASA has launched a multi-satellite mission called MMS to try to unlock the secrets of our magnetic field.
The MMS mission is a mission consisting of 4 spacecraft which will fly in close constellation to measure a process called magnetic reconnection.
The universe is full of plasma and it's full of magnetic fields, and all over the place in the universe you have one plasma colliding with another. An example of that is the solar wind coming in and colliding with Earth's magnetosphere. And then the magnetic energy in the plasma, some fraction of that magnetic energy is converted very rapidly into plasma energy. So you can think of it as kind of like a magnetic explosion. And the reason this is important is because these explosions drive a lot of the weather patterns that we see in the magnetosphere, and so what space scientists like to refer to as space weather. And these space weather phenomena can have impact on our everyday lives. It can actually affect communication satellites, the power grid. So we'd really like to understand how these magnetic explosions work.
We need to measure reconnection in more than one location. We need to measure it in basically how it varies in space, how it varies in all 3 spatial dimensions. And that requires a tetrahedron. The additional fantastic benefit that provides is that it will actually enable us to recognize that we are looking with a reconnecting region much easier than a single spacecraft.
The ideal situation is that we would like the 4 spacecraft to kind of be surrounding this region where the explosion is happening. So the separation of the spacecraft is about 10 to 100 kilometers, which may seem like a long distance. But in terms of the magnetosphere, which is absolutely huge, this is really a microscopic region that we're trying to cover.
MMS has, in a nutshell, 2 orbital phases which are designed to study reconnection.
On the day side, basically you have a situation where the solar wind is just constantly running into Earth's magnetic field. And this is really great for MMS because we know that at some point MMS is going to encounter this region, and our hope is that since this process is always happening, we're going to get lucky and actually fly right through the magnetic explosion as it's happening. Now on the night side, the situation is a little bit different. So what happens is you have a more gradual buildup of magnetic energy in the tail, and these reconnection processes, these magnetic explosions, can just sort of pop off randomly. We don't really know when it's going to happen or where it's going to happen in the tail.
We need to understand both of those if we want to understand how the magnetosphere works, and we believe that both of those scenarios are also very important for other applications, such as on the Sun, in the solar wind, in planetary magnetospheres, and in many astrophysical objects, as well as in the laboratory.
We hope that it's going to allow us to improve our models so that we can put the right physics in it and actually make predictions about where and when reconnection is going to happen, and this will help us make our space weather models more predictively powerful. The instruments that are actually going to be measuring the particles in space are collecting them much more rapidly at a much higher cadence than they have on previous missions, about a factor of 100. So whereas it would take a previous generation particle instrument about 3 or 4 seconds to build up a whole picture of the sky, it's going to take MMS about 30 milliseconds. So it really is sort of game-changing technology.
The current 24 or so operating satellites will be enhanced with new missions under development. The Japanese Space Agency will be launching their next solar physics satellite, Solar C. The Indian Space Agency will be launching Aditya to study the Sun's coronal mass ejections and magnetic field structures. The Deep Space Climate Observatory will maintain real-time solar wind monitoring capabilities critical to the accuracy and lead time of space weather alerts and forecasts. The European Space Agency's solar orbiter will be launched in 2018 and fly closer to the Sun than the planet Mercury to study how the Sun creates and controls its heliosphere. Also planned for a 2018 launch is NASA's Solar Probe Plus. It will approach the Sun more closely than any other probe before, at just 3.8 million miles from the surface of the star. Scientists have long wanted to send a probe through the Sun's outer atmosphere. The spacecraft will be exposed to temperatures approaching 1,370 degrees Celsius. Together, they will continue to monitor, study, and discover the secrets of this nuclear anvil that supplies us with light and life. Aside from the science, the images captured reveal to us the beauty and power of this, our nearest star, in all its grandeur. The night sky is a time machine. The further we look out into the universe, the further back in time we reach. What we see in the night sky is only a small percentage of the contents of the universe. Most is dark matter and dark energy. We know it exists, but its nature eludes us for the moment. No longer hampered by a hazy, often polluted atmosphere, telescopes and other sensors have been able to obtain clearer images from orbit thanks to advances in technology and engineering. In the 1960s, satellites began to explore the cosmos surrounding us. They saw beyond visible light into ultraviolet, infrared, X-ray and even gamma rays. Like the universe itself, our understanding of its beginnings, construction, evolution and future is evolving and constantly expanding. In the last 2 decades of the 20th century, the United States and other nations began to develop more substantial research programs, utilizing larger and more complex space-based telescopes.
For hundreds of years, thousands of years, humans have thought the universe is a very static place. If you go out at night and look into the night sky, you will see that things don't really change much. The universe appeared very static for a long time. We now know this is not true. The universe is a highly dynamic place, and things are happening all the time. Every single second, a star explodes in a gigantic supernova explosion somewhere in the universe. And we have to go and find it. We have to build instruments that are capable of finding those unforeseen events.
The Cosmic Background Explorer, or COBE satellite, started crystallizing the big picture of the universe by mapping the microwave background radiation left over from the early universe. Its successor, WMAP, created the most detailed portrait of the infant universe.
Well, because it takes the light over 13 billion years to reach us, we are seeing now what the universe looked like then, over 13 billion years ago. So it's a fossil remnant of what the early universe was like. And just like fossils are used to study the past, we use this light to study what the universe was like way back near the very beginning.
And you can see in there blue spots and red spots. And what those correspond to are slightly hotter and colder images of the sky. That's a picture there, those hot and cold spots, that pattern is really it's the afterglow of the Big Bang. On a sort of deeper, long-term time level, it's this amazing consistency that the picture we can put together of the universe is relatively simple, that the pieces fit together. It's a stunning confirmation of the study of cosmology for many years now. It's just built up, and here it is. In some ways, we're getting to know the cosmos like we know our own backyards.
ESA's Planck spacecraft joined the fleet and expanded on their observations. Together, they were able to map vast regions in multiple wavelengths, enabling astronomers to determine the size, shape, and age of the known universe.
Just 370,000 years after the universe began in a Big Bang, all that existed was a hot plasma similar to a candle flame. Protons and electrons, seen as the red and green balls, were bouncing around, scattering the light. The particles of light, called photons, shown in blue, couldn't go far without colliding with an electron. As the universe cooled, the protons and electrons could pair up, forming hydrogen atoms, and the light was free to travel. It's been traveling freely ever since, through the dark ages before there were stars, then past the formation of the first stars. As the universe expanded, photons lost energy, changing color. They went past clusters of galaxies. The path of the photon is slightly bent by the gravity of the clusters. Now and then, going through a cluster, an electron, that green ball, would collide with some of the photons. They would change their path, past more matter, more little wiggles due to gravity and mass. The photons traveled for 13.8 billion years before they reached the Planck detectors and died a glorious death, giving up the information that they had gleaned passing through the entire universe to our instruments and enabling us to make this beautiful map of the universe.
The various satellite telescopes have sensors designed for use in multiple wavelengths of the electromagnetic spectrum, from near to far infrared light, through visible and ultraviolet frequencies, to X-ray, gamma, and cosmic ray detectors. Each can reveal unique aspects of the construction of stars, nebulae, galaxies, and the exotic blazars and black holes. However, in the public's eye, the poster pin-up star of the latest generation would undoubtedly be the Hubble Space Telescope. Over its 25-year lifespan, Hubble has produced some of the most amazing imagery of the cosmos as it delves back in time through visible and infrared light. Another advantage of Hubble is its long lifespan, thanks to several maintenance missions, which allows it to study objects over a long period of time with some amazing results. Newborn stars eject streams of matter into the surrounding star-forming region. Known as Herbig-Haro objects, these supersonic jets can be seen to change over a very short time span.
If you see just a single picture from Hubble, you can interpret it in many different ways. But the fact that Hubble has been around for as long as it has been means by taking multiple images, you can actually stitch them together and watch how the material moves. And so that really gives you the only way to get true insight into the physics of the dynamics of what's going on.
The Horsehead Nebula in the Orion constellation, silhouetted by glowing gas, is a good example. Infrared can see right through, revealing its dark secrets. The Spitzer telescope is one of NASA's great observatories.
Spitzer is an infrared telescope, which means it sees through the dust that's out in space. And by seeing through the dust, we get to pinpoint the stellar nurseries that are out there where stars are being born.
We've been flying for about 10 years. That's about 3,600 days. We have 5,000 published papers. That means every day a new paper based on Spitzer data announcing new results and new discoveries is published, which to me is absolutely amazing.
Spitzer has made several surprising revelations within our solar system and beyond. It helped pinpoint some of the most distant galaxies in the universe, and Spitzer's ultra-high-resolution map of the Milky Way substantially improved our understanding of our own galaxy's structure. Japan and ESA had launched their own infrared telescopes in various infrared wavelengths. The European Herschel, in particular, focused on massive star formation regions.
We are really happy to have new things and to understand, trying to understand, because we are making a new step towards our understanding of massive star formation. So the idea is that Herschel can reveal this population of highly embedded stars that are formed in a gas and dust cocoon, but that are not visible at optical wavelength, for example. So we need Herschel to detect all this population of very young stars.
The next great spaceborne infrared telescope is the James Webb Telescope, which is nearing test completion in preparation for its launch in 2018. It will have a 6.5-meter primary mirror, almost 3 times larger than Hubble. However, ground-based telescopes are also working in the infrared spectrum.
So there's a large complementarity between space and ground. From space, with the Hubble images, you can characterize the images, you see the images much better. With the ground-based telescopes, you then can take that light and look at spectra and then find the redshifts, for example, for distant galaxies, or you can take infrared observations, which Hubble couldn't do for a long time, to then see how these objects look in the infrared.
Together, they have delved into the star-forming nebulae left over from exploding supernova and witnessed the birth of stars. Another observational tool in the electromagnetic spectrum for astronomers and cosmologists is the X-ray band.
An amazing discovery of the last 20 years is that every galaxy, like our own Milky Way, has a massive black hole at its heart. And as material from this galaxy, dust and gas, falls onto this central black hole. It radiates, and we can see that. So if we look at the sky in visible light, we see stars. If we look at the sky in X-rays, we see black holes.
You can observe X-rays from very distant objects. So you can investigate the cosmic structure of the universe. So you investigate the matter distribution in the universe via observing the galaxies, the black holes in the center of the galaxies to very far distances. And this is very important for cosmology and to learn about the origin and the evolution of our universe.
X-rays are absorbed in our atmosphere, so X-ray detectors must be placed at either high altitudes by balloon or into orbit. NASA's flagship X-ray telescope and one of their great observatories is Chandra.
If you want to find black holes, you want to use an X-ray telescope.
What we're tending to find is that a cluster of galaxies has a bright central galaxy in the middle. It's often an active galaxy or a quasar, so a supermassive black hole in the middle of a big galaxy. Because when the cluster is forming, a lot of the material tends to fall to the middle, so you get the biggest galaxy in the middle.
So you see the power of an observatory, an observatory like Chandra with a state-of-the-art telescope and these imaging and spectroscopic capabilities of its science instruments can do things that maybe weren't even things that you planned on doing because you didn't know about them at the time. And a lot of the science with Chandra falls in that category.
The most recent telescope launched is NuSTAR, which has the ability to focus X-rays for a much sharper image. One of NuSTAR's main scientific goals is to make a full census of black holes in the universe. X-rays have also revealed the explosive processes of nova seen only at these wavelengths. ESA have their XMM Newton studying cosmic evolution, and Integral, the International Gamma Ray Astrophysics Laboratory, looking at gamma ray frequencies, revealing unseen structures and new sources of gamma rays.
So Integral is important because it's one of the few satellites which look in gamma rays. And together with other satellites and observatories around the Earth, you can get a complete picture of how these stars evolve. And without Integral, you're missing a large piece of the puzzle. We want to know how did they produce the elements which we are made of. And these are the objects which throw all the different kinds of material into the universe, and they wander off into space. And we are made of all these elements which are produced by the supernova. So it is important for us to know where does life originate and how does it originate.
Gamma rays are at the top of the electromagnetic spectrum, the most energetic and powerful photons which stream from black holes, exploding stars, and even from our own star, the Sun. Originally called GLAST, the Fermi Gamma Ray Space Telescope observes the entire sky in high-energy gamma rays every 3 hours, creating the most detailed map of the universe ever known at these energies. When it detects a new gamma ray burst, it works in conjunction with the SWIFT satellite. Then SWIFT is able to spin rapidly across the sky and point an X-ray telescope and an optical ultraviolet telescope at the possible location of the gamma ray burst.
GLAST is primarily devoted to seeing in a new energy range.
It's designed to pick up at the upper end of the SWIFT energy range and carry it on up to much higher energies.
And it allows you to just see, stranger and more exotic things the further up in energy that you go.
GLAST and SWIFT are very different. SWIFT is like a nimble small satellite that points here and there, but it isn't surveying the whole sky, it's pointing in its particular objects. GLAST looks in the high energy gamma ray sky, and looks over the whole sky at all times.
So when we see something interesting with GLAST, we can ask SWIFT to go look at it with their other telescopes and gain additional information about it.
We don't know what will happen over the next 10 years, hoping that SWIFT will still give us exciting data. But what we do know is that SWIFT will give us exciting new data because of its pure nature. This is what it was built for, to study new, unforeseen, unexpected events. And they will inevitably happen.
There is one more type of radiation being studied in orbit: cosmic rays. The 8-ton cosmic ray particle detector, called the Alpha Magnetic Spectrometer or AMS instrument, is attached to the International Space Station. Cosmic rays consist of protons, alpha particles, atomic nuclei of heavier elements, electrons, their antimatter partner positrons, and gamma rays. Studying these particles may answer some fundamental questions, like the unexplained absence of antimatter and the nature of dark matter in the universe.
Calibration of positron is important because when you have dark matter collision with another dark matter, you produce excess positrons. So the characteristics of the excess positron tells you what's the origin of dark matter.
About 80% of the matter in the universe is invisible to telescopes. This dark matter neither reflects, absorbs, nor emits light, yet it interacts with matter via a gravitational influence which can be seen in the orbital speeds of stars around galaxies and in the motions of clusters of galaxies. Yet, despite decades of effort, no one knows what this dark matter really is. This visualization shows galaxies composed of gas, stars, and dark matter colliding and forming filaments in the large-scale universe, providing a view of the cosmic web. It is believed that dark matter provides the framework for this web. Galaxy clusters are the largest gravitationally bound structures in the universe. It is also believed that after the Big Bang, the universe originally decelerated in its expansion, but then changed gears and began to accelerate.
Important discoveries in astronomy and astrophysics was the discovery of dark energy, and that is that the universe is accelerating apart. What people are trying to do using various different techniques, and again in all the different wavelength bands, is to measure the parameters to characterize the dark energy.
With a launch date set for 2020, ESA is building Euclid, a space telescope which, it is hoped, will chart dark matter and dark energy's effect on the universe.
I'm working on Euclid. That is a mission to map the universe. And for that we built a highly precise telescope in which we can map dark matter structures as well as derive the properties of the dark energy.
Understanding dark energy will allow us to understand the future of the universe.
The interesting thing is we get more and more dark energy. Why? Because our universe is expanding. And with our expanding universe, we get more dark energy in our universe. Now, the ordinary matter, so dark matter and normal matter, is not expanding, it's diluting. So the fraction of dark energy compared to normal matter is increasing in time. When the universe expands more and more, we get more volume of our universe, we get more space, and we get more dark energy.
The leading particle physics model for dark matter is called weakly interacting massive particles, or also known as WIMPs. These guys just fly through the universe without even bumping into anything or each other. The idea of two WIMPs coming together, annihilating and forming gamma rays is kind of like two bullets hitting head-on in a crossfire. It's very rare. But when you go to the area around a supermassive black hole, we expect the density to be much higher, so the probability of annihilation is much higher in this detection with a gamma ray telescope.
In his theoretical process, Schnittmann's computer simulation shows particles of dark matter around a massive spinning black hole. All of the action takes place close to the black hole's event horizon, the boundary beyond which nothing can escape, in a flattened region called the ergosphere. Within the ergosphere, the black hole's rotation drags space-time along with it, and everything is forced to move in the same direction at nearly the speed of light. Concentrated, fast-moving dark matter particles collide and make gamma rays, but only some of this high-energy light can escape the black hole, in this case from the left side, where the black hole is spinning towards us, giving us a lopsided glow of high-powered gamma rays. The simulation tells astronomers that there is an astrophysically interesting signal they may be able to detect as gamma-ray telescopes improve. Schnittmann believes this would be conclusive evidence of the WIMP model.
To me, dark matter, black holes, two of the most elusive things in the universe coming together to help explain each other is quite poetic.
Future missions will see a gravitational wave observatory to study gravity waves and test Einstein's theory of general relativity. The Athena mission, mapping hot gas structures and searching for supermassive black holes, due to launch in 2028. The Sloan Digital Sky Survey, the most ambitious astronomical survey ever undertaken, will provide a three-dimensional map of about 1 million galaxies and quasars. The recently refurbished and upscaled CERN Large Hadron Collider is one of the tools in search of WIMPs and other exotic particles that may help explain the fabric of the cosmos. Then perhaps the scientists, astronomers and engineers can turn their attention to other mysterious theories brought about by particle physics, such as multiple dimensions, entire universes beyond our own, and what lies beyond the event horizon. These in time will become the new frontier. From the beginnings of our solar system 4.5 billion years ago, there remain tantalizing clues to its evolution. Remnant debris, asteroids and comets. They vary in size from grains of dust to mountainsides, from footballs to planetoids. They were the building blocks of the planets and perhaps carry the origins of life itself. Now within our grasp, these rocks of ice and dust are ready to give up their secrets. Asteroids are believed to be made of chondrules, flash-heated grains of rock within the stellar disk of our forming solar system. These chondrules clustered together, forming the first asteroids and the building blocks of the planets. Once the solar system had evolved, there was a lot of asteroid material left over. They cover a broad spectrum of types. The largest of these are minor planets or planetoids, large enough to have an ovoid shape. This category took the previous planet Pluto off the major list and onto the minor. The smallest remnants of debris are often called meteoroids. There are in fact several minor planets. Some have been seconded into planetary orbit and become moons. The traditional asteroid belt between Mars and Jupiter has one called Ceres, the largest and the first to be detected. Our first close-up of an asteroid was courtesy of Galileo on its flight through the main asteroid belt towards Jupiter. It photographed 951 Gaspra, an S-type asteroid with an average diameter of just over 6 kilometers. The S stands for stony composition. Galileo then photographed the larger 243 Ida at 15.5 kilometers wide, revealing that it has its own moon named Dactyl. Asteroids are not limited to the asteroid belt between the orbits of Mars and Jupiter. Many orbit much closer to Earth and are known as near-Earth objects, or NEOs.
Radar is a very powerful instrument that we use to study near-Earth asteroids. Asteroid Toutatis was millions of kilometers away, and we were able to resolve surface rocks. We could see boulders.
There are currently only 2 radar facilities in the world that have sufficient sensitivity for doing regular observations of near-Earth objects: Arecibo and Goldstone.
Even the most powerful optical telescopes, and I'm talking even, Hubble telescope, they can only see this asteroid as a point of light. It is just too far and too small.
It provides an extraordinary opportunity to get very detailed radar images.
You are transmitting microwaves. It's propagating at the speed of light toward the asteroid. It is bouncing back. And this radar echo is containing surface features of the asteroid. It's telling us about its rotation, and it's very precisely pinpointing its distance from the radar.
These asteroids were imaged with ground-based radar. BL-86 revealed it has its own moon, and asteroid HQ-124 passed very close to Earth, some 3¼ times the distance to the moon. It is due to return sometime in the 24th century. Scientists are looking much more closely at these objects for their potential to pass through Earth's orbital plane and perhaps pose a threat. The most common type of asteroid is the C-type carbonaceous, accounting for about 75% of known asteroids. The probe near Shoemaker was the first dedicated asteroid probe launched by NASA. It photographed 253 Mathilde, a C-type, then moved on to 433 Eros, the largest visited at the time, where it orbited, took extensive measurements, and, more by accident than good planning, landed on the asteroid, the first probe to do so. Deep Space One, an experimental NASA probe, was sent to investigate an asteroid 9969 Braille. Technical errors returned poor imagery. However, the probe continued on to its second rendezvous, for the first time with a comet, 19P Borrelli. Comets are closely related to asteroids, but originate from the cold, dark outer boundaries of our solar system.
Comets are bodies in our solar system that have been left over ever since the solar system formed, some 4.5 billion years ago. And therefore, when we look into comets, we look into the past of our solar system. And so by investigating the details of comets, how they formed, how they evolved, we can actually have a glimpse into how our solar system formed, and in the end, how the Earth formed and why we are here.
Comets have been recorded throughout history, as they are easily observed when close to the Sun, often considered an omen. One comet of note was Halley's. In 1986, Halley's comet returned once again, and this time it was met with a veritable armada of space probes. The first attempt at a space rendezvous was with the International Comet Explorer, or ICE. It passed through the tail of comet 21P Giacobini-Zinner on its way to meet Halley. The European Space Agency sent Giotto. The Russian and French sent 2 probes via Venus, Vega 1 and Vega 2. Japan sent Suisei and Sakikage, that country's first deep space probes. Their measurements went on to refine the targeting for Giotto to make a much closer pass of the comet's nucleus than first planned. In 1994, astronomers and scientists were given an unexpected treat. Comet Shoemaker-Levy broke apart and struck Jupiter in a spectacularly violent fashion. Comets required more study. The Stardust probe was dispatched to investigate 5535 Anne Frank, Wild 2, and then the Tempel 1 comet. It returned a sample of cometary tail to Earth.
Our biggest discovery that we did was looking at this cometary material that was returned from NASA's Stardust mission. And the Stardust mission went up, rendezvoused with a comet, brought back very small amounts of material, comet material and comet exposed material. We had basically one shot at looking at this, and it was really pushing our limits of detection. So I spent about 2 years optimizing our technique, really rehearsing, practicing, getting everything as perfect as possible before the one day of doing measurements. It's sort of all leading up to one big game, one big day. And also just working with meteorites and working with the cometary material, I'm working with something that's 4.5 billion years old that very few people ever get to play with, and the few days of being able to do the actual measurements make up for all of the rehearsals that it takes.
JAXA launched Hayabusa to study asteroid 25143 Itokawa and to retrieve a sample from the surface in a touch-and-go maneuver. The mission took a total of 7 years to accomplish, with the sample return pod retrieved from the Australian outback in 2010. Launched a year earlier by the European Space Agency was a very ambitious spacecraft called Rosetta. Its goal? To land a probe on a comet, 67P Churyumov-Gerasimenko. Just getting there was to prove a challenge in astronavigation.
But when you want to rendezvous with a comet, you have to accelerate the spacecraft and match the same velocity that the comet has around the sun. So this is the problem, not only the distance, but also the velocity. There is no rocket that can give us the velocity needed to be as fast as the comet. Like close to a planet, and you use the gravitational attraction of the planet to actually accelerate your spacecraft.
It passed by asteroids 2867 Steins and 21 Lutetia.
Lutetia is a very strange target, a very strange asteroid. We believe that it may be a C-class asteroid, which means that it is very primitive. However, it shows from ground-based and also spaceborne observations that Lutetia does not look completely like a C-type asteroid, and we are really puzzled about what it really may be.
The spacecraft then moved on to its primary target, Comet 67P.
The nucleus is pulling the spacecraft out of its planned orbit, and that can be seen as a shift in frequency of the transmitted radio signal from the spacecraft. And the extent of this frequency shift is a measure of the mass of the comet nucleus, so we are able to weigh the nucleus here.
There is no ice at the top, so it's covered by a mantle that we consider is essentially made of organic material. That's why it's very dark. And this material is one of the key things we would like to explore and analyze.
These organics may hold the secret to life on Earth.
What it's all about is the carbon chemistry. How much did the comets bring to Earth? So was it just the right elements, the right building blocks, or was there more information in it when these comets already arrived?
To try and answer these questions, ESA attempted one of the most daring missions mankind has ever undertaken, to land a probe on the surface of the comet. Landing on a comet is one of the hardest things that has ever been done by the human species.
This is the comet. It's roughly a 1 in 1,000 model, so the real thing is 1,000 times bigger. The landing site is roughly here, which we're aiming for to deliver the lander. It's the flattest part we could find. What we are studying at the comet with the instruments are basically what are the ingredients, which materials are present, and coming back to one of the objectives of the mission, how complex are the materials present at the comet.
Landing means flying very, very slowly over the comet and then gently pushing away the lander. It's not a landing like you can imagine on the moon, where you come with rockets and you have to brake. Here the problem is the opposite. You have to really touch gently the comet. The forces involved are very small.
If I get meaningful data, that would be just marvelous. If the descent works, the landing is okay, we receive a sample, and the whole thing runs smoothly, that would be just great. But we need a lot of luck, really. And we had a lot of luck already.
So we are sitting on the surface. Philae is talking to us, more data to come and to be analyzed right now. Going down, which it should do, of course. We are there, it's done its job. We are on the comet.
The science has started now. We have the first results that give us the first comprehension of what we think the comet is, where it started from. Now, for the rest of the year, we'll watch how the comet evolves. We'll unlock how the comet works. We're looking at where the gas and the dust start to accelerate from the surface and how that beginning of the coma, that birth of the coma works. So how the coma develops as it does to higher altitudes. This region has only ever been theoretically constrained or modelled. These will be the first measurements we make in this area or this region, and that's a really big, important target for us.
Eventually, the tiny probe shut down.
Having Philae reactivated is not so likely, but it's not impossible. Philae was designed to hibernate, was designed to switch off and be able to reactivate itself. Of course, we expected this to be a duration of a few days or a few weeks, not a few months. But okay, we will see. Maybe we are lucky and the units have survived these months and will reactivate in June, July.
While observing the asteroids, scientists were surprised to find one with what looked like a cometary tail. After careful study, scientists realized they were observing the results of the impact of two asteroids. 596 Sheila had been struck at high speed by a small asteroid. The impact hit with the force of a 100-kiloton nuclear bomb. NASA had done something similar with Deep Impact, a probe sent to Comet Tempel 1, where it dispatched a kinetic impactor which struck the comet to study the impact and the debris thrown up as a consequence. Soon after, NASA launched another small ion-powered probe, Dawn, which also had an extraordinary mission: to travel deep into the asteroid belt between Mars and Jupiter. Its targets, two of the largest asteroids in the solar system. Dawn rendezvoused with 4 Vesta and orbited it for over a year, returning a wealth of data. Dawn then departed and cruised towards Ceres, the largest of the asteroids, a planetoid, where it has obtained orbit and begun its study. JAXA, the Japanese space agency, has recently launched a second Hayabusa probe, this one with many improvements over the first. Its target is the C-type asteroid 1999 JU3. It's expected to reach its destination in 3 years, collect samples, and return to Earth by 2020. NASA has announced the OSIRIS-REx sample return mission to asteroid 1999 RQ-36, better known as Bennu. It's expected to launch sometime in the near future, and after a 2-year journey, orbit and map the surface before touching down to retrieve 2 kilograms of material. The probe sample's return is expected in 2023. There is also a practical reason to study asteroids. In 2013, an asteroid with a mass of about 9,100 tons exploded over Chelyabinsk, Russia, with the force of 20 Hiroshima bombs, causing 1,500 injuries and damaging 7,000 buildings. It isn't the first asteroid strike on Earth, as the dinosaurs can attest to, and probably not the last. Through the United Nations, ESA and other major space agencies have established a safeguard program.
The NEOWISE data have returned 2 very important findings. First, we've been able to determine that we've found 93% of all the near-Earth asteroids that are out there that are larger than 1 kilometer. We've also been able to tell that there are somewhat fewer near-Earth asteroids that are larger than 100 meters than were previously thought. However, fewer does not mean none. That leaves about 15,000 asteroids larger than 100 meters that remain to be found.
This advisory group is also planning intervention missions if needed.
We think that we can cope with deflecting an asteroid with 2 different technologies mainly. One is what we call kinetic impactor, hitting the asteroid and pushing it out of the way. The second one is take a heavy spacecraft and use it as, say, a gravity tractor. So by the mass of the spacecraft, you pull the asteroid away.
There is one project in the planning stage to snag a small asteroid in the near-Earth region and drag it into a lunar orbit. There it can be met by astronauts aboard an Orion capsule who will study the asteroid firsthand, take extensive samples, and return to Earth. For the more we know, the better prepared we are to protect our place in the solar system. The orbit between us and our star, hidden within the sun's glare, often visible only at sunrise or sunset. Venus, the first and brightest star in the evening sky, and Mercury fleeting across the solar disk. They are half of our solar system's terrestrial planets, yet we know so little. As we begin to take a closer look at our companions, they are posing more questions than answers. This is Mercury, the innermost planet closest to our Sun. Mercury's days are longer than its years, and it has an elliptical orbit from 47 million kilometers at its closest point to 70 million kilometers. Difficult to observe from Earth due to the Sun's light, Mercury is an enigma of the solar system's evolution.
Well, Mercury is really a weird planet. Normal terrestrial planets, all the rest, have a relation between how big they are and how dense they are. Mercury is not following that rule. It's much more dense than what you would expect for its size. That is not normal, so something went wrong in the formation of Mercury that we don't know.
Only 2 probes have been sent to investigate the planet, and only one has achieved orbit. Mercury is difficult to get to because of its orbital speed and the gravitational influence of the Sun.
Mercury, for us, is a planet of extremes. So you have temperatures like 400, 450 degrees on the surface during the day, and imagine that's like being in a pizza oven on Earth. So it's really hot there, and temperatures at about minus 175 during the night.
Mercury orbits the Sun every 88 days in an atypical elliptical orbit. At its nearest approach to Earth, it is 77 million kilometers away. The first close-up imagery of Mercury came from the US probe Mariner 10 in 1974. With insufficient fuel to slow the craft, it was not possible to put the probe into orbit. Instead, it orbited the Sun, passing by Mercury 3 times. The flybys provided 2 interesting observations. Firstly, Mercury has a magnetic field similar to Earth, which is unusual due to the very slow spin of the planet. Secondly, the surface of the planet showed extensive cratering and very little volcanic or crustal movement. 2 contradictory observations of why the planet has such a magnetic field. The second and most recent probe is Messenger. Launched in 2004, it made several planetary flybys of Earth, Venus and Mercury to slow down to the correct speeds. It took 6.5 years to reach Mercury and enter orbit in 2011.
Because of this short distance from our central star, the temperature of the planet is very, very high. And when you want to fly around Mercury with a satellite, you find yourself in a very special thermal situation where you get a lot of heat coming from the planet itself that behaves like a thermal mirror. And then from the side you get the heat from the sun. So you have two heating sources which may destroy a normal spacecraft. Another NASA mission, Messenger, is getting operational in a very loose Mercury orbit because, as I said, the thermal situation is such that you better stay away from the planet.
Its primary mission was completed within a year, mapping the entire globe with about 100,000 images. With fuel in reserve, the mission life of the probe was extended. After 10 years, Messenger continued to send back information and observations. Magnetic field data, the magnetosphere, the effects of solar wind plasma, and studies of the atmosphere of Mercury. It is so low in density it is constantly blown off the planet as an exosphere, revealing the likes of sodium, calcium, and magnesium in a trailing tail away from the sun. Spectrographic imaging of the surface material has thrown up more questions about the high metallic density of the planet. The observations do not fit the standing theories of the planet's evolution, which will have to be completely overhauled. One other interesting detail: at the north and south polar regions, Messenger has detected the presence of water ice in the permanently shadowed interiors of craters, just like on our Moon. In 2014, the probe was tasked to fly much closer to the surface, as close as 50 kilometers. There it imaged the surface at much greater resolution, hunting for more detailed signs of the planet's geological history. Left unaided, the probe continued to descend and ultimately impact on the surface. There was, however, sufficient fuel in reserve for 3 trajectory alterations to increase altitude and give the probe a short time extension to continue its work into 2015. A third mission to Mercury is underway by the European Space Agency and the Japanese agency JAXA. Bepi Colombo is named after the Italian mathematician Giuseppe Bepi Colombo, who first developed the gravity assist maneuver for NASA with the Mariner 10 probe. It consists of 2 orbiters, the ESA Mercury Planetary Orbiter and the Japanese Mercury Magnetospheric Orbiter.
What scientists want to do is try to understand the nature of the planet itself. What material is on the surface. We would like to measure temperatures. We would like to see the interaction with the solar wind. Then Mercury has a magnetic field, which is like Earth, a dynamo field. We would like to understand that.
The Japanese MMO will focus on the magnetic field environment around the planet, while the ESA probe will focus on the planetary surface. Like the previous 2 probes, Bepi Colombo will use Earth and Venus to slow the probe's speed down to drop closer to Mercury's orbit. This trajectory will take approximately 7 years to accomplish, With solar electric motors to maintain deceleration, then a conventional rocket engine will be used for orbital insertion. The orbital life of the probes in the harsh environment is expected to last 1 to 2 years. The two craft carry a suite of the most advanced instruments, including a laser altimeter and magnetometer, infrared and ultraviolet spectrometers, imaging X-ray and high-resolution stereo cameras. Bepi Colombo is designed to answer specific questions about this planet. Why is the planet so dense? How did it form? Is the planet tectonically active? Why can no iron be identified on the surface? In the absence of any ionosphere, how does the magnetic field interact with the solar wind? How is the magnetic field generated?
We have a theory to understand how planetary systems form. Now, the theory was based on explaining the solar system, and it was fine, it worked. But now, when we have discovered new planets around other stars in the galaxy, the extrasolar planets, they don't fit at all. So something is wrong. And the special cases, those that are difficult to understand in the details, like Mercury, are very helpful.
By finding answers to some of these questions, Bepi Colombo will help us understand how the solar system was formed 4.5 billion years ago. It is the first and brightest star you see at night. Our sister planet in some ways, our closest planetary neighbor in both distance and diameter. However, Venus is difficult to reach and a very strange world when you get there.
In the early days of the solar system, Venus and Earth must have been very similar. But then something happened and they took a different route in its evolution.
Venus is the only planet in the solar system that needs more time to rotate once around its own axis than it rotates around the Sun. There must have been a major disaster in the early history of the planet where it collided with a big other object. And this made it stop its rotation. The problem is that without the protection and without the rotation, the planet lost its water and so it's completely dry. And this, in the end, led to a horrible greenhouse effect that caused the temperature to rise to the levels that we see
One of the main differences between Venus and the Earth is simply that Venus doesn't have a magnetic field. So the way it interacts with the star is completely different. If you want to understand how did Venus get that way, why does Venus not have any ocean, you need to understand the interaction between the star and the planet.
The Soviet Union and the United States sent probes with some success. 3 Mariner spacecraft made brief flybys, and the Soviet Veneras entered the atmosphere and touched down, some surviving for minutes. They managed to send back tantalizing images of an almost serene vista. NASA sent 2 more probes, Pioneer Venus 1 and 2, the latter depositing 5 small probes onto the surface. The Soviets continued their program of Venera probes with 4 successful landers and orbiters. A further 2 Russian Vega missions deposited atmospheric probes as they swung by en route to Halley's Comet.
The atmosphere of Venus is incredibly interesting because it's so different from the Earth's atmosphere. And we'd like to understand what causes these differences, because this might well help our understanding of climate change on planet Earth.
There's a very dense atmosphere, to 97% of carbon dioxide, a very strong greenhouse effect, and the temperature down on the surface is more than 450 degrees Celsius. and the surface pressure is 92 bars. It's almost 100 times more than the Earth. So it's a very, very unpleasant place to be.
High up in the clouds, about 100 kilometers from the surface, the wind speeds are very, very high. The wind is traveling at 300 kilometers an hour, and it travels around the Earth, around Venus every 4 to 5 days. So that's one of the things we don't understand, why at the surface the winds are very gentle, and high up the winds are very, very fast. So it's a very different atmosphere to the Earth's atmosphere.
0 and liftoff of Space Shuttle Atlantis.
In 1989, the NASA probe Magellan was launched from the payload bay of Atlantis en route to Venus, its 5-year mission to radar map the entire planet's surface. The radar managed to peer through the dense atmosphere and revealed the true face of Venus. What it showed was a young surface with few craters and mostly covered with volcanic activity, lava flows and large lava plains. Surprisingly, there was little evidence of wind erosion, and the surface plate tectonics were dominated by global rift zones, unlike Earth. To date, that was the last Venus probe from NASA. It was 12 more years before Venus came under scrutiny again, this time by ESA's Venus Express. To conserve fuel for a long mission, the probe utilized aerobraking in the Venusian atmosphere to make orbit.
Very interesting discoveries of Venus was a huge vortex, a huge cloud at one of the poles of Venus that in some ways looks very similar to a hurricane on the Earth. But this is a long-standing event that's there all the time. We don't understand how it's formed, why it's there, and how it will evolve.
When we arrived at Venus 8 years ago, we detected winds at 300 kilometers per hour, very fast. But what has happened during these years, until now, they have actually increased. We now see winds of 400 kilometers per hour. And we can't really explain why that has happened.
More questions were raised by the planet's absent magnetic field.
Venus doesn't have a magnetic field. So Venus is just this big rock with this atmosphere and the ionosphere sitting in space, and the supersonic solar wind with the interplanetary magnetic field whacks into Venus, and it can't penetrate through the ionosphere. So the interplanetary field lines just sort of pile up ahead of Venus, like cars on a freeway. This solar wind whacking into it essentially sort of strips off the atmosphere, and it literally forms this long tail, like a comet that's stretching out into space. Pioneer Venus Orbiter was the first spacecraft to really thoroughly explore that night side region where the atmosphere is all escaping away, and it discovered this really mysterious phenomena which has yet to be explained. Imagine that we're flying from pole to pole on the night side, so we're feeling the plasma around us, and then suddenly the ionosphere disappears, and then it sort of comes back. And this is what an ionospheric hole is. It's like a chasm in the sky, a big hole where the ionosphere is just absent. So Pioneer Venus Orbiter basically measured inside these things, and we saw that there is very little plasma, and there's all this magnetic field. And from that, they sort of suggested that this is essentially a magnetic structure that's sitting in the night side. I wanted to see if I could go looking for these things with Venus Express. What we saw is essentially this really exciting, strong, straight magnetic field lines that we expected, and really boring plasma signatures. It shows us that this is a magnetic structure, right? This is a tube of interplanetary magnetic field that, well, PVO saw it coming out of the ground, and now we've seen it way out in the tail. So these things really continue out to much higher altitudes than we previously have found them at.
As Venus Express neared the end of its mission, scientists made some risky aerobraking maneuvers to bring the probe much lower in orbit to make close-up observations of the planet. These maneuvers involved daring plunges into the hostile atmosphere only 130 kilometers above the planet's surface.
For the aerobraking, we wanted the most area possible to get the most friction possible, but that also generates heat. And so what we did was we went into the atmosphere in this direction, because this face of the spacecraft, which had been attached to the rocket originally when it was launched, was most able to take the forces and the temperatures. We also turned the solar panels so that the side with the actual solar arrays was in the back to maximize the area as we went through the atmosphere, to maximize the amount of friction and to get the most amount of braking. What we saw that was a little unusual is the variability in the pressure, as if there were waves within the atmosphere. And so that possible wave-like structure was not expected, and analyzing that data will keep scientists busy for a little while yet.
Venus Express carried a suite of 7 instruments: magnetometer, spectrometer, and several cameras to study the atmospheric winds and surrounding space environment. Venus Express outlived its planned 2-year mission by another 7, and only recently was it directed to ditch into the planet's atmosphere. The Japanese have made the most recent attempt to reach Venus with Akatsuki, whose planned observations are to include cloud and surface imaging with infrared cameras. Their main focus is the Venusian meteorology, including confirming the presence of lightning and any current volcanic activity. The probe failed to enter orbit on its first attempt, and JAXA are hopeful when the probe's heliocentric orbit returns it to Venus that a second attempt will succeed very soon. There are many plans afoot to return to Venus. Even a manned mission has been studied by various groups. One such study conducted for NASA produced HAVOC, a high-altitude Venus operational concept. It would rely upon 2 spacecraft sent into Venus orbit, the first unmanned atmospheric descent stage and the second orbital return craft carrying the crew. They would dock, transfer crew to the descent stage, and proceed to deorbit. Once into the upper atmosphere, a parachute would deploy, slowing the descent and allowing the deployment of a dirigible craft to inflate and carry the crew at high altitude. From there, they would study the planet below. The return journey for the crew would begin with a high-altitude launch back into orbit, where they would dock with the orbiter, transfer crew and equipment, and then make the journey back to Earth. There they could dock with an Orion capsule for the return to Earth. In the cold, dark expanse of our solar system, beyond the asteroid belt, lie the giant planets. Some can be seen with the naked eye, others only glimpsed once by a passing probe. We are again sending cameras to the edge of the solar system to bring us new insights into the evolution of our worlds. Pioneer 10 and 11 made the first passage through the asteroid belt, leading the way for the venerable Voyager missions. These two probes made a grand tour of the outer solar system before slipping away into interstellar space. Jupiter, the first and greatest of the outer planets with its broiling sky, has had fleeting visits from other missions like Ulysses, Galileo and Cassini, each adding to the mosaic of Jupiter and its violent atmosphere.
My name is Amy Simon Miller, and I study the atmospheres of the Jovian planets. Weather on Jupiter is confined to a rather thin layer kind of high up in the atmosphere. So the tops of the clouds are what we're seeing when we look at Jupiter. One thing we're seeing in the southern part of the equatorial region is little V-shaped clouds or chevrons, and we wanted to understand how those are moving in the atmosphere.
What we think chevrons are simply holes in the clouds. They are simply areas where we don't see any bright white clouds.
The Cassini mission flew by Jupiter in the year 2000, and because it was a slow, distant flyby, we got a lot of coverage of the planet over a long time period. So we were able to put those images together and make movies.
Using these movies, we observed Rossby waves that caused north-south meanders in a jet stream south of the equator. With new movies, we instead focused on hotspots. Hotspots are unique because we believe that there is a Rossby wave similar to what we previously detected, but instead of this Rossby wave moving north-south, it primarily moves up and down in the atmosphere. The downward portion of the wave pushes air down into warmer layers of the atmosphere. This causes any clouds that are embedded within the wave to evaporate and prevents further clouds from forming. So at any given time, there are approximately 8 to 10 hotspots in Jupiter's atmosphere that are spaced roughly evenly apart from one another. We believe that each of the downward portions of this Rossby wave corresponds to the hotspots that we see on Jupiter. This new finding is exciting because it'll allow us to re-examine the Galileo probe data and allow us to better understand it and better place it in the context of Jupiter's overall global climate and atmosphere.
The latest probe to be specifically aimed for Jupiter is Juno. Launched 2011, the probe will reach Jupiter after a 5-year journey. Juno's goal is to investigate Jupiter's interior structure and magnetosphere and help improve our understanding of the formation of the planet and therefore the history of our solar system.
Juno spins like a propeller, where the propeller is kind of facing the sun because they're all solar powered.
If you spin something, it stays spinning. It's like a gyroscope. We can use a spinning spacecraft to let each instrument get its turn to see Jupiter. We get to go very close to the planet, inside the radiation belts instead of outside the radiation belt. We're in a polar orbit, so by small adjustments of the timing, we can map the entire planet. We can get repeated stripes at different longitudes as Jupiter spins underneath us.
It does mean that Juno is going to see the polar regions to a greater extent than with other spacecraft. But I think the most important thing is that it gets in very close to the planet as part of that ellipse brings it in a few thousand miles above those cloud tops, very close, near the equator.
We're going to go over the poles of Jupiter. That means we can study the magnetosphere in a different way.
A magnetosphere is the sphere of influence of a magnetic field. So a planet that has a magnetic field has a magnetosphere when its sphere of influence extends beyond the planet out into space and affects the region around it. The magnetosphere of Jupiter is vast. So if you think of Jupiter being 10 times the size of the Earth, and the magnetosphere is 100 times the size of Jupiter.
The Juno probe is the furthest NASA has sent a solar-powered spacecraft. Sunlight provides 25 times less energy than on Earth, which means it requires advanced solar power technology with solar cells which are both 50% more efficient and more radiation tolerant than silicon cells. The craft also houses an electronics vault, which is radiation shielded to protect the electronics aboard from the intense and deadly radiation environment around Jupiter. The probe carries a full set of sensors: a microwave radiometer for atmospheric sounding and composition study, plasma and energetic particle detectors, a vector magnetometer, a radioplasma wave experiment and ultraviolet, and an infrared imager, plus a color camera called JunoCam.
In Roman mythology, which of course is rooted from Greek mythology, Juno was the wife and sister goddess of Jupiter. And Jupiter was sort of being naughty with some friends, so he cast a veil of clouds around himself and his friends. But of course, Juno was a fairly powerful god herself and used her powers to look right through the clouds and see the true nature of Jupiter and understand what he was really up to. And that's exactly what the Juno spacecraft does for us, is that it goes there with special instruments in a special orbit and uses its powers to see right through Jupiter's clouds and understand its true nature, which is holding these secrets for us about how the solar system formed and where we all came from.
A long-standing feature of the storms of Jupiter is the Great Red Spot. Large enough to swallow the Earth, this storm system has been studied since the 19th century. Then it was measured at a little over 41,000 kilometers on its long axis. Voyager 1 and 2 measured it at over 23,000 kilometers, and recent observations by the Hubble Space Telescope have the red spot at only 16,500 kilometers long. It seems the rate of shrinkage is increasing. One day it will probably vanish altogether. Juno will also help confirm the theory that Jupiter was the first of the planets in the solar system to form from the primordial disk of dust and gas some 4.6 billion years ago.
I would expect Juno to tell us more about how planets work, meaning how the heat gets out, what kinds of flows exist inside the body, how magnetic fields get generated. Learning what Jupiter is made of, we will learn such a wide range of things. For indeed, Jupiter is the most massive planet in the solar system. It is the body you want to understand in order to understand the architecture of everything else, including Earth.
Juno's year-long mission will end with a deorbit burn and a slow descent into the upper atmosphere, where it will continue to send back scientific data until its destruction. Perhaps the jewel of the solar system is Saturn, with her spectacular rings. All four of the outer planets have rings of ice and rock, but Saturn's is the most complicated, and, with thousands of ringlets, the most visible. There are several groups of rings classified A through to G. Some are formed by shepherd moons within the rings, and by gravitational tidal effects from others outside. Yet some gaps are still unexplained. The current spacecraft at Saturn is Cassini on its second extended mission, the Cassini Solstice mission, which is expected to be completed in 2017. It continues to watch the planet-sized storms in the atmosphere.
Great white spots on Saturn are these large storms that erupt about once every year on Saturn. A year on Saturn is 29 Earth years. The great white spot that erupted in December 2010 initially presented itself as a small little white fluffy cloud that came up, and various instruments on Cassini were seeing it, and ground-based instruments seeing it as well. And as the days progressed, the storm got larger, and then it got sheared from the top and the bottom of the storm on either side of it, and it wrapped all the way across the planet. We'd never before been able to study a storm system of this magnitude in the infrared, so we are very fortunate at this time to have a spacecraft in orbit and excellent ground-based facilities, allowing us to make a historical record of this great white spot. And that will allow us to compare it in future generations when the next one happens.
Another phenomenon is a hexagon of clouds around the North Pole of Saturn, which has recently come into the light.
Cassini has been in orbit around Saturn for 9 years, and we've been following this hexagon which surrounds the North Pole. It's bigger than 2 Earths, and it's a wandering jet stream. But it's been winter in the north, so we have not been able to see what's at the center of the hexagon. But now it's spring, and what we found at the center of the hexagon is a Saturn hurricane. This is a view from directly over the North Pole, which is made possible by the orbit of the spacecraft, which is now taking us over the poles. The winds are flowing at 300 miles an hour, which is 4 times hurricane force. The fluffy white clouds in the center are about the size of Texas. We can use special filters to measure the heights of the clouds, and the red are low clouds and the green are high clouds. We call it a Saturn hurricane because it has the eye, it has the high winds, but it's different from an Earth hurricane because it's locked to the North Pole. And unlike a terrestrial hurricane, there's no ocean underneath. And that's one of the puzzles we're trying to figure out.
A phenomenon first observed on Saturn by Pioneer 11 in 1979, and common to Earth as well, are polar auroras. These magnetic-generated light shows are far more spectacular on Saturn, rising hundreds of miles above the planet's poles. And unlike on Earth, where bright displays fizzle after only a few hours, auroras on Saturn can shine for days. Auroras are produced when speeding particles, accelerated by the sun's energy, collide with gases in a planet's atmosphere. The gases fluoresce, emitting flashes of light at different wavelengths. The Hubble Space Telescope has been watching them closely.
starting in 2016, ending in 2017. These orbits will take us up and over the north and south poles of the planet.
We're actually going to dive in between the innermost edge of the D-ring and the upper atmosphere of the planet itself.
From that, we're going to learn how is Saturn constructed from inside out.
We'll also get the magnetic field of the planet, the mass of the rings for the very first time, and get to sample a place that no spacecraft has ever flown before.
This is a mission that cannot be duplicated. So we really want to take advantage of this opportunity to observe seasonal variation in the system.
Uranus has had only one visitor from Earth, Voyager 2. Like the other gas giants, Uranus has a ring system, a magnetosphere, and numerous moons. There the similarities end. Images from Voyager revealed a featureless atmosphere with no cloud patterns or storms. Uranus differs in its orientation as well. Tilted onto its side, its poles lie where other planets have their equators. Its magnetosphere is off-center and tilted as well, generating an unusual asymmetrical field. This causes Uranus's auroras to be well off the poles. Observations from Earth have shown seasonal change and increased weather activity as Uranus approached its equinox in 2007. The wind speeds on Uranus can reach 250 meters a second. Although there are currently no scheduled missions to Uranus, there have been several proposals put forward, both jointly from ESA and NASA and JPL, including both nuclear and solar-powered probes and an atmospheric descent probe. Ion propulsion is favored because it allows a greater mass to be sent to the planet. Ideally, a probe could be launched in 2020 with a 13-year cruise to Uranus. As this is considered a low-priority mission, no funding has yet been allocated. The eighth and last planet in our solar system is Neptune, the last of the gas giants. Made of hydrogen and helium, it has trace amounts of methane, which gives the planet its beautiful blue color. It too has only been visited once by Voyager. The detailed images taken at that time revealed white clouds and a massive storm marring its atmosphere with supersonic winds.
The storm revolves around the planet every 18 hours. And then it rotates around its own axis like a big glob of pizza dough every 16 days.
Voyager also identified a ring system and confirmed 14 moons. Triton is its largest and is believed to have been captured by the planet from the outer Kuiper belt. Voyager also discovered Neptune's magnetic field was off-center and tilted, not unlike Uranus. Both Uranus and Neptune have had very little close-up study, and various missions have been proposed to fill the gap in our understanding of these ice giants. NASA has looked into several possible missions back to Neptune, perhaps a similar probe design to that of Cassini-Huygens, but due to fiscal and other constraints, none have been approved.
The Voyager mission to the outer planets has certainly been a journey of a lifetime. Having encountered Triton as the last world we would visit, I don't see how any of the scientists could have been happier.
Next stop was Pluto. When New Horizons was conceived, built and launched, Pluto was still a planet. The downgrade to dwarf made little difference to its investigation.
Well, you know, the key to planetary science is that you really have to go places to get the resolution, to get up close enough to really see what's going on. We want to get up close and personal.
New Horizons is the first really of a whole new breed of spacecraft that is focusing on a very specific task.
For this mission, the questions are basic. What do Pluto and Charon look like, and what are they made of?
We had to really be disciplined and say, we can't do everything. Let's focus on the primary questions and design the instruments to answer those primary questions.
New Horizons was built light and launched on a very powerful rocket, breaking all previous speed records when it left Earth on a solar escape trajectory at 16.26 kilometers per second. The spacecraft passed the orbit of the Moon in just 9 hours. It then cruised for just 1 year to reach Jupiter, where it was given a gravity boost, increasing its speed by 2 kilometers per second and cutting the travel time to Pluto by 3 years. New Horizons was the first to visit the dwarf planet and Charon, its largest moon. Pluto failed one of the 3 criteria to remain a fully fledged planet. It has not cleared the neighborhood around its orbit. Pluto is part of the Kuiper Belt and not the only dwarf planet residing there. This is an image of Pluto at its closest approach. It still remains a treasure trove of scientific questions and hopefully answers about the origins and evolution of the solar system. From Pluto's flyby, it is on to the unknowns of the Kuiper Belt. The most numerous objects in the solar system are the ice dwarf planets that make up this donut-shaped region on the edge of the solar system.
It's kind of like the asteroid belt, but much bigger. It has hundreds of times more objects in it than the asteroid belt.
The spacecraft will visit some of these objects in its travels.
Once you have the orbit, and we know where the spacecraft is and where it's going to be, we can figure out how much fuel the spacecraft is going to need to use to get to these objects.
After some careful calculations,
it looked like we might actually have to burn the engines to miss the object, which was a pretty exciting concept. You know, it's a good thing we looked, because you wouldn't want to run into one of these things.
These cold classicals, they're pretty much as they were 4.5 billion years ago. They're little fossils. That's incredible. We have no idea what they're going to look like.
New Horizons will continue to explore the outer solar system until 2026. The sky above is studded with stars and countless galaxies. In them we can read not only our origin, but also our final destination. The first phase of our journey is complete. We are ready to undertake the second. With robotics, advanced technologies, and sheer daring, we are now going to places that before we only dreamt we might ever reach. It was here at Peenemünde on the Baltic coast where the opening shots of the space race were fired. Not an auspicious occasion, The backdrop to this extraordinary effort was World War. The chief engineer did mutter, however, the rocket functioned perfectly, it just hit the wrong planet. Time and tide have changed that frontier. Now science and commercial imperatives lead the way. Our push into the new frontier is now genuine and humane, guided by science and the hunger for discovery. Soon it will be underpinned by the commercial realities of tourism and mining. Research and engineering advances are ongoing. New communications and sensing technologies, new space systems for advanced aerobraking, new materials and manufacturing processes for new spacecraft, and safer launch systems. All aimed squarely at a return to the moon. Then, on to Mars for a long-term stay.
The human flight component would like to see an experiment where resources on the surface of Mars, from the rocks or the atmosphere, could be used to generate fuel or other parts that would enable future exploration in cutting the tie, so to speak, to Earth. So you wouldn't necessarily have to bring everything with you. You can actually manufacture it on the planet. And that's a really exciting additional component that we've been exploring and analyzing in this work.
This will extend our reach even further, with planned excursions to the asteroids and comets giving us access to even greater resources. At the same time, it would help us protect Earth from wayward objects posing a threat to our planet. Then there is the challenge of the greater solar system, visiting the outer planets and their moons. Jupiter's Europa, Callisto, Ganymede. Or Saturn's Enceladus, a potential life-harboring location. Or cloud-covered Titan, which holds vast hydrocarbon resources. Then, the great interstellar voyages to other stars and other planets. Like HD 189733b, a gas giant. Or Gliese 1214b, a water world. Or even Kepler 186f, a nearby Earth-like planet. Our first stop in this journey takes us into orbit, where we can continue to look down at the world's changing environment and study the planet we call home. We humans are mere passengers on board this vessel called Earth. We cannot control the direction she takes, how fast she spins. But we can influence her complex and dynamic ecological climate engine. To study this machine that sustains us, scientists have used satellites as one of their primary tools. Of the 6,600 satellites launched so far, some 3,600 remain in orbit, with only 1,000 still operational.
There are two main sorts of satellites that we use for weather forecasting. The first sort is the geostationary satellite. Now, these geostationary satellites are launched into orbit at 36,000 kilometers above the Earth's surface. And at this height, they orbit the Earth precisely once per day. I can illustrate it like this. The Earth rotates around its axis on a 24-hour basis, and at the same time, the satellite orbits the Earth. So it always stays over the same point of the Earth. In this way, it takes an image of the Earth now with our MSG series every 15 minutes, and it can provide very high rapid update cycles from that data. The other main sort of weather satellites we have are the polar orbiters. Now these orbit the Earth at a much lower altitude, about 800 kilometers, and they orbit pretty much over the North and South Pole in what we call a sun-synchronous orbit. Now, because they're much lower down, they're able to provide us with a much more detailed view of the Earth and the atmosphere.
The complexity of the Earth climate model is due to a range of variable inputs, from solar radiation, solar winds, magnetic fields, gravity, thermal absorption, to water temperature and salinity, ice and cloud coverage, carbon dioxide and other trace gases in the atmosphere, to name just a few. The first order of business has been to monitor our weather. Maximum scientific value comes from long-term data gathering. It has to be reliable, continuous and uninterrupted. To this end, ESA and EUMETSAT have launched their latest satellite, METOP-B.
METOP-B is particularly important to provide continuity of this data. This data has the largest single impact into the weather forecasting system. So it's very important that we maintain this capability, and for climate purposes it's very important that we maintain a continuous record in time.
Apart from accurate weather data, it also carries a GOME, or Global Ozone Monitoring Experiment. It monitors ozone concentrations in the polar regions.
This is an instrument that measures in the ultraviolet and visible part of the spectrum to retrieve information on the ozone structure in the atmosphere, which is particularly important for understanding the recovery of the ozone hole, and also it's now used within weather forecasting itself.
Weather forecasting is important for everybody because weather impacts a large amount of society, economic aspects. It impacts everyday's life. Satellites improve weather forecasting, so improved forecasting enables us to provide earlier warnings, better warnings, give us more time to warn.
There is now a concerted and coordinated effort by the major space agencies, NASA, ESA and JAXA, along with their international partners, to launch a series of next-generation Earth observation satellites, each with specific instrumentation to address the many variables making up our climate. Joint partners NASA and the Japanese Space Agency have launched an international satellite mission, GPM. The Global Precipitation Measurement Mission will set a new standard of observation of rain and snow worldwide. GPM consists of a core satellite with 8 constellation satellites. With precipitation radar and a microwave radiometer, the system will collect global data every 3 hours.
The GMI produces a critical reference standard which unifies all the member satellites of the GPM constellation. The instrument has 13 channels, and this greater sensitivity allows GPM to measure a greater variety of precipitation type and intensity. Each channel has a frequency range that can detect a different type of precipitation. Scientific algorithms then translate the GMI's brightness temperature data into more meaningful products, such as rain rates. Because GPM's coverage extends beyond the tropics, measuring storms like these in the mid and high latitudes will improve and expand the global view of precipitation.
Conducted with the National Oceanic and Atmospheric Agency and the space agencies of France, India and China, the GPM mission data will advance our understanding of the water and energy cycles and extend the use of precipitation data to directly benefit society. Two major components of Earth's climate system are the water cycle and ocean circulation. The joint US-Argentinian Aquarius Satellite de Aplicaciones Científicas mission can map the salinity or the concentration of dissolved salt at the ocean's surface. By measuring ocean salinity from space, Aquarius will provide new insights into how the massive natural exchange of fresh water between the ocean, atmosphere and sea ice influences ocean circulation, weather and climate. One of the oldest and most venerable satellite missions to date is Landsat. A NASA and US Geological Society project begun in 1972 with the launch of the first Landsat satellite, it is the longest-running contiguous Earth imaging program. The 8th of the series is currently in orbit.
It orbits over the North and South poles, taking imagery on the sunlit side of the Earth every time it passes.
The Landsat 8 satellite makes 14 orbits per day and covers the entire globe every 16 days.
The data from the Landsat data continuity mission will be the best data that have ever been collected from a Landsat satellite. With the increasing population, our land use are changing at rates unprecedented in human history. To manage and cope with these changes, we need to have the observations, the information, the data that allow us to understand what's going on the surface of the Earth where most of us live.
The data collected over 40 years of the Earth's surface has created an historic archive unmatched in quality, detail and coverage.
Landsat archive that contains all of the US-held data from all of the Landsat satellites, and the LDCM data will become part of that archive.
The Landsat program offers, free to anyone, the longest global record of the Earth's surface, and it will continue to deliver visually stunning and scientifically valuable images of our planet. However, the Earth's surface is predominantly water. Measuring the topography of the oceans is another challenge altogether. Begun by the Topex Poseidon satellite, a joint effort of NASA and France's Centre National d'Études Spatiales, and continued by the Jason-1 satellite, their latest mission is Jason-2, continuing to provide a long-term survey of Earth's oceans. It measures changes in the height of the sea's surface. These are used to understand shifts in ocean currents as well as sea level rise, both critical parts of global climate change. The data is used around the world to improve weather, climate and ocean forecasts. Another ocean-going measurement is the speed and direction of the winds. The Sea Winds Scatterometer is a specialized microwave radar that measures near-surface wind. The scatterometer estimates wind speed and direction over the Earth's oceans at 10 meters above the surface of the water. The instrument collects data over ocean, land and ice in a continuous 1,800-kilometer wide band, making approximately 400,000 measurements and covering 90% of Earth's surface in one day. Earlier satellites could only image the uppermost layers of clouds. CloudSat was among the first satellites to study clouds on a global basis. It looked at their structure, composition and effects. The key observations are the vertical profiles of cloud liquid water and ice water contents and related cloud physical and radiative properties. CloudSat flies in tight formation with the Calypso satellite, carrying a backscattering LIDAR, and these two satellites follow behind the Aqua satellite in a somewhat looser formation.
When we started with airs on Aqua, we had two goals defined to us, before the mission started. One, provide data to the nation's weather forecasting center, which is NOAA, and improve weather forecasting. So that was the first goal achieved, and we, the science team, felt good. The second goal was improve our understanding of the climate system, the water vapor. That is the main mechanism by which weather and climate is formed here on Earth.
The combination of data from the three satellites provides a rich source of information that can be used to assess the role of clouds in both weather and climate. The European Space Agency's Earth Explorer program has seen several high-tech satellites play their part in our understanding of the global climate.
We have launched 3 missions, meanwhile, with fantastic results and very innovative technology.
SMOS, the Soil Moisture and Salinity Satellite, observed soil moisture over the land and salinity in the oceans. Cryosat, the ice mission, measured the thickness of the massive ice sheets over Greenland and Antarctica and the marine ice in the Arctic. It used a sophisticated stereo radar system and has helped give us a better understanding of the relationship between ice and global warming. GOCHE measured Earth's gravity field with unprecedented accuracy. A geoid model is crucial for deriving accurate measurements of ocean circulation and sea level change, both of which are affected by climate change. This data revealed the Earth to be lumpy and quite variable across the planet. It has led to a new map of the boundary between the Earth's crust and mantle. Another piece in the climate puzzle, and a critical one, is the Earth's magnetic field.
The Earth magnetic field is our lifesaver. There's no doubt about this. This shield is basically protecting us from the harmful effect of the solar wind, these high energy particles that the sun is constantly bombarding us with, and this shield is really essential for us and for our protection. The main magnetic field of the Earth is changing in time, and it is weakening by a factor of, let's say, 10–15% or so over the last 200 years. And what's actually going on in the outer core of the planet is what we really try to find out. The magnetometer package on board SWARM, it measures the magnitude and also the direction of the Earth magnetic field. And it does so in 2 locations. One, it has an instrument at the tip of the boom and also another instrument halfway down the boom. And together, they give all this precise information that we needed to decipher the secrets of the Earth magnetic field.
ESA is now developing a new family of missions called Sentinels as part of their Copernicus program.
It is not sufficient to monitor the evolution of the ice cap or to monitor the sea level rise during 5 years and then stop. We really need to monitor those things over a very long time period. And this is what Copernicus will bring. It will bring a long-term frame for continuous monitoring of our environment.
Sentinel-1A is the first of a 2-satellite mission that will scan land and oceans using advanced radar to deliver imagery regardless of weather.
Copernicus is the most ambitious Earth observation program to date. The European Space Agency is putting together 6 families of Sentinels that will take care of the objectives of the Copernicus program, monitoring the land, the marine environment, the atmosphere, climate change, and providing a fast response to security and emergencies.
In total, there will be 6 Sentinel missions, each pair of satellites devoted to specific observations.
Each Sentinel has a specific duty. Sentinel-1 is more specifically tailored to emergency response. Sentinel-2 is focused on monitoring of the land. Sentinel-3, together with Sentinel-6, is focused on the monitoring of the ocean and waters. Sentinel-4, together with Sentinel-5, is specially tailored to the monitoring of the atmosphere.
The International Space Station is also host to several climate sensors. Currently, the CATS, or Cloud Aerosol Transport System, is mounted on the Japanese experiment module. Using light detection and a ranging LIDAR system, it detects and measures pollution, dust, smoke and other aerosols in the atmosphere. NASA will be installing another instrument, the RapidScat, onto the end of the station's Columbus module this year. It will measure ocean surface wind speed and direction, and help improve forecasting and hurricane warnings. The Orbiting Carbon Observatory was NASA's first satellite dedicated to the tracking of carbon in the atmosphere, how it is reabsorbed into the biomass, and where. Unfortunately, a launch failure has caused a reschedule of the project.
But we need the measurements that spacecraft like OCL will make in order to understand the processes controlling the rate of buildup of carbon dioxide in our atmosphere so that we can understand how it will change in the future.
Other projects in motion include the Atmospheric Dynamics mission Aeolus with its high-power UV laser, which will measure wind speed, air moisture and dust particles to advance our understanding of atmospheric dynamics. EarthCare will study how the Earth reflects and traps heat. Biomass will study the state of the Earth's forests. NASA's Clario satellite will measure incident solar irradiance and the Earth energy budget. SMAP, the Soil Moisture Active Passive, is an Earth satellite mission designed to measure and map Earth's soil moisture and freeze-thaw state to better understand terrestrial water, carbon and energy cycles. The suite of satellites now in orbit and planned for the near future will be able to peer beneath the clouds, vegetation and other surface features, monitor water salinity, temperature and energy fluxes, chart ocean currents and the change in ice caps. All this data is helping to improve our understanding of climate change and also helping in a practical sense, with flood and drought monitoring, hurricane and cyclone warnings, understanding changes in water availability, food production, and the other societal impacts of climate change.